If not, we can have the conversation. When it reaches the 15, you mean?
Yeah, it's 15. But
yeah. I plan to. I plan for 15. Yeah. So if It's okay now.
No, it's
Okay.
it's okay. So you are screen sharing, so everything you do it here. I can put the first one that is
the first one that is
okay.
Okay. Okay. We can
And
start.
then put it in full screen mode.
Yep.
Okay. Yep.
Okay.
It's already there.
Okay.
Yeah. Okay. So
Thank you, Miguel. We know where you are. So am I supposed to be in front here or you don't know?
The camera is here. You can pick up you here,
Yeah,
here,
whatever you want.
or wherever.
Okay.
So you can see it right there.
Yep.
Where the
Should I put the pointer now?
if you want to put.
Yep.
Yeah.
Sorry.
Try to connect it here.
Very good.
Yeah.
Thank you. Yeah, perfect.
Yeah. Try it if it's all working okay. I will.
Welcome to this second parallel session on earthquake and geotechnical engineering. The title of the first presentation is Geotechnical Seismic Isolation Technology with Rubber Soil Trenches for Earthquake Resilience of Existing Structure. The presenter is here, Joan Bernal Sanchez. Thank you. No more than 15 minutes and a couple of questions later. The floor is yours.
Thank you very much. Thank you very much, everyone, for attending the presentation. I know we need a bit of geo presentations. We've had a lot of wind, so we are going to break the ice a bit with this presentation. So I'm representing Edinburgh University in Scotland. There's not been any earthquake registered yet, except for the concert of Taylor Swift last year in the Murrayfield Stadium. So I'm just saying that this is the only real experience that we have with a tremor. But this is an investigation that goes back to 2010. And we started actually with some of the people who coined or used this terminology of GSI. So I don't know if you've heard about it. Maybe some of you have already even done some testing. This is a really good opportunity because we are bringing to fruition what we've tested theoretically, thanks to obviously the positive institution, the Aristotle University of Thessaloniki, but I've got the collaboration of all the universities in Scotland, Strathclyde University, University of Dundee, and ourselves. If you want to connect with us, I mean, we're always welcome to creating some of the kind of investigations. So if you want to scan the QR code, if not, afterwards we can have a chat. We don't only do geotechnical earthquake engineering solutions. We also look at more, I would say, more micromechanics. So we look at particle-to-particle interaction, maybe something that is overlooked when we look at geo-earthquake engineering, but that is also relevant. And I'm going to try to show it here today in this presentation. Bit of the background, probably most of us, we know about this. 17 major earthquakes taking place yearly with over 20,000 casualties as an average. Most of these casualties take place in areas where there's construction materials of very poor quality or inadequate planning. So those are the two main characteristics of this type of events. And although there's existence of some kind of rubber bearings or other kind of base isolation systems, yeah, this is an AI created image. Some of you are wondering how we came up with that. So we know that medium or low to medium rise structures are the one that suffer the most. We know that most of these catastrophes are taking place in the developed world or developed countries, and 90% of earthquake fatalities are taking place here. And it becomes a bit of a snakes and ladder process where these countries try to develop, try to emerge, and try to construct all these big cities, but they don't do it in the right way or in the right order. And then they come up with this inadequate planning, inadequate use of the materials, and tend to lead to these catastrophic events, as I would say. We've got the case of the 2023 Turkey earthquake, Syria earthquake. It was very catastrophic. Somehow everyone got affected by it, directly or indirectly. What we know after the experience is that the characteristics of these structures led to those failures, and most of it is because of the inadequate use of lateral bracing, inadequate use of shear force walls, the use of open spaces, and that created or led to some kind of pancake type of failures of the ground floors, and there were numerous catastrophes in this case from the structural point of view. So in a way, just trying to summarize this, there are earthquake resistant technologies that are out there, typically expensive, require a lot of knowledge, require a lot of design, implementation, and in a way is difficult to implement in these developing countries. So why am I here today, or why this group of investigation came up, is to try to come up with a solution to justify and to implement into these areas so that the energy coming from these earthquakes can be mitigated before it reaches the structure. All those points that you see there at the bottom are impossible to tackle, but it's the idea, no? Trying to look out for something that is easy to deploy, that is inexpensive, that can be applied to both historical and residential buildings, and preferably sustainable. Those are the kind of things that we all look for in a way. So GSI, as I say, is a term that was coined in 2009. Kim Fosang is part of this investigation as well, and is trying to change the ground conditions in such a way that we can somehow dissipate and mitigate these incoming waves before it reaches the structure. We did a very rough comparison between structural and geotechnical elements. We'll see something like this, where we have a flexible base, similar to what you will find with a laminated rubber bearing, or on the right, more what we call a geosynthetic linear that works as a friction and dissipating energy, as you will see in the structures with the spherical sliding bearing. This group of investigation has been around since 2010. We've been part of over 100 publications and also part of special issues and special sessions in World Conference and the European conferences. And next year we're going to be as well in another European conference. So we are growing, no? And there are more people that are trying to look at different type of branches of the solution. If we try to simplify and we try to look at the three main branches of this kind of GSI systems, we look at solid structural interaction, so this will be more a flexible base. We'll have what we call the sliding base, or on the third area, on the right side, we'll have what we call the wave scattering. So that's the one I'm going to focus on today. There are numerous publications. As I said, most of these studies have been focused on trying to look at the element and particle scale, so not so much about the macro behavior, and that's where we are moving with investigations like this one. There's been, as I say, other type of investigations where they are more relying on the friction between the materials, and the wave scattering is the one that is trying to mitigate or to reduce the stress coming from the input energy before it reaches the structure. There's been already some studies done on site, as you can see here today, with the use of other materials, geofoams and expansive polyurethane that can be implemented into the soil, but they are still in infant stages, and we need to justify its use in more permanent, long-lasting type of solutions. And that's why Eries and this kind of investigation is so fundamental. The kind of rationale and the theory behind the use of ground trenches has been there since 1968 from the theoretical point of view. They are used commonly for the mitigation of ground-borne vibrations. Most of them rely on the equation of the impedance ratio. And what we see is that there's some kind of ranges in terms of the normalized depth, normalized width of those trenches that come up with a better design configuration. So elements such as trench depth, width, location to the source, input frequency, all those kind of factors we need to take into consideration when we look at the design configuration. So some of the publications, I'm sure that there are some people here who work with those investigations, are trying to look at different ways of installing the materials into the soil in such a way that it can better attenuate the incoming vibration. So specifically, the main objective of this project was to come up with a GSI solution with the use of rubber soil mixtures that I'll try to cover a bit more right now here, in order to be able to be implemented into earthquake-prone regions. So it follows the category of the research code 3, the built environment, and the research activity 4A for new technologies. The different material properties have been widely studied in the literature. In this case, we were using rubber and sand, Leighton Woods and sand that is commonly used in the UK. And we've seen that with the addition of the rubber, the stiffness tends to reduce, obviously because of the use of this deformable material. But there's an improvement in the damping capacity of the mixture because of combining friction and deformability of the rubber. Also, one of the things that we've investigated is the different factors, the different particle properties that actually lead to changes in dynamic properties. They are numerous. We're talking about the shape, the size ratio between the two particles, the confining pressure, relative density. There are many aspects that actually lead to different changes and different results in the macro behavior. And we have seen that it's quite beneficial is that actually by adding this rubber, we can retard the accumulation of pore water pressure and liquefaction potential in areas that could be highly saturated. And we've seen that there's an enhanced internal stability. We've seen this by applying factors and equations such as the gradient entropy coordinates, where we look at that kind of particle-to-particle interaction. We also did some X-ray tomographic tests, and we see that actually because of the fissures and cracks of these rubber particles, they deform, they change the volume, they stick to each other, and when there's a rebound, or in this case cyclic loading, actually they recover the shape. That's the reason why they have an enhanced internal stability, and they are good under this kind of cycling continuous aftermath conditions. So just focusing specifically on what's going to be this publication, we did some shaking table tests. It looks a miniature compared to the shaking table test that we just went to visit, but you have to think that this is our custom-built shaking table test. We did it ourselves. And what we saw, or in this case, we tried to look at two different trenches added around a structure to look at the peak accelerations around that point. And what we found is that there was some significant attenuation in certain conditions, mainly around the resonance frequency of the input soil, in this case, this lithium butcher sand. We actually found that there was a significant reduction in the upward acceleration, factors that were important in this case and that we think that are going to be difficult to achieve on real site conditions were the relative density of the trench. So we saw that actually by increasing the relative density of the trench, we could reduce more and more the peak acceleration that we were getting on top of the structure. Now, going back to what's going to be the real test, because believe it or not, we haven't done the test yet. We still have a few months before this funding runs out. So the plan is that we do the testing at the end of this month. It's going to be in Thessaloniki. We are going to build up on what Dimitris Pitilakis did in 2021, in this case with this prototype structure with the steel bracing and the concrete at the top and the bottom. In their case, what they did was to put the mass shaker on top of the building to try to look at how those frequencies and how the accelerations are transmitted. And in their case, they added the material, in this case, gravel rubber mixture, a different type of geomaterial under the building to look at that kind of flexible base to see if there's some kind of reduction in the results. In the accelerations, in this case, we can see that, for example, with the addition of 30% of rubber, there was some lengthening of the video of the structure, and there was a clear reduction in the upward acceleration. So we want to move from there instead of just being implemented before we place the structure on top, which will limit the application of this kind of technology to new infrastructure. We want to add a trench of this gravel rubber mixture next to the building for those already existing infrastructure, which will be good to understand. So for that, we did a series of final element modeling simulations before we do the actual on-site test by looking at what happens when we add a mass shaker at certain distance from the simulated building. And we look at actually the transmission of those accelerations. By looking at the normalized amplitude reduction ratio, what we've seen is that actually the addition of both the 30 and 100% of rubber, in this case, it will be just recycled rubber that is added into the trench. We see that there's another important attenuation of the acceleration. We've seen that in this case, one critical factor, as is being mentioned in the literature, is the depth of the trench. In the case of the width, maybe it's not that relevant. We've seen that there's an upper limit around 0.5, 0.6 meters that it's more than enough. We don't need to go beyond that. And we have seen that it's the range of influence is correlated to the depth of the trench. So in this case, the deeper the trench, the farther away is the influence of this kind of trench. In some instances, for example, when we went down to 6 meters depth, we've seen that actually there's amplification, and there's also amplification in front of the trench because the incoming wave is rebounding and actually creates an amplification of the signal. In terms of pseudo-spectral oscillation, we've seen the same kind of reduction in the values. In this case, we've looked at a range that goes from 5 hertz to up to 60 hertz, and we've seen the same. When we go deeper into the trench, we get actually a greater attenuation of the signal. As you can tell here, at 5 hertz, at lower frequencies, we will see sometimes an amplification, which is not what we are looking for. So that's why this design configuration will require a lot of calibration, and that's what we want to see as well on real site conditions. But we are getting much better results than in the literature, and I think that is because of the use of this type of material that is well studied, and also because of the site conditions that are well studied. So these two graphs are representing what we think we're going to see on real site conditions, because we've adapted them to the actual trench configuration. And as I said, I think that we're going to see really positive results in most of the frequency range, both lower and higher frequency spectrum. Just to give you an idea of the kind of challenges that we will have to face, obviously, with the inclusion of this kind of material, we need to think about excavation depth, width, how we are going to do it, how we are going to contain the material, the kind of geotextile we need to put in place, how we are going to remove it, how we're going to do all those tests within 1 week, because we want to test different types of materials. Also, the proximity to the building, if that's going to have some kind of influence in the stability of the trench. As you go deeper, obviously, you will have to maintain the walls of the trench, and that's something that we might not be able to do on this occasion, but we want to see how far we can go in terms of depth. Those kind of things are the kind of issues that we will encounter with the configuration of such a test. This is a plain view of what's going to be the actual testing with the monitor, in this case, the use of triaxial accelerometers and seismometers to measure acceleration and velocity. And we are going to look at 2 different aspects. The ground monitoring, looking at the ground surface and the accelerations over distance. We are not going to look only at the same line. We want to also look at a radial distance and see how far it can be the influence of adding this type of trench. And we are also going to do some structural monitoring by looking at things like rotation, drift, or changes in the position of the building. For that, we've got the help of a company Structura that is coming all the way from Mexico City, and they have really good experience in monitoring for the structural response. So it will be very good to have them on board. Just trying to conclude, we've seen with this shallow type of trenches, with the addition of these rubber mixtures or gravel-rubber mixtures, we can see some attenuation in accelerations, and it's promising to see that this is also compared with some finite element simulations. We've seen that in this case, the same factors that have been placed for ground bore variations, rubber content, trench depth, width, and spacing can also be somehow varied and studied in our investigation. This proposes or comes up as a solution or an alternative to those kind of technologies that can only be put into new structures. So it will be also applicable to existing structures. And thankfully, thanks to this on-site testing, we'll be able to compare the great work we've done so far. Thank you very much.
So much. Thank you for being in time.
Thank you.
There's some curiosity from or question. Please, Guido.
And thanks for the presentation. Mine is a curiosity when it comes to seismic isolation to rubber. Do you take into consideration density, how it can change by shaking? Is there any specific measurement that you can do or you've done? Or
so you mean that in this case, by having a loose material after shaking it, what happens with the density?
Even through shaking, how the soil can react to, because of the density can change depending on pressure. So is there any done, or is there in the literature? I'm not an expert of seismic isolation through technical.
We, in terms of the specification, we've seen that if the material is loose, and actually I've got a video there that I can show you just very quickly. If you just give me 1 second. You can see kind of like what happens with the material when you test it. So if it's in a loose state and it's not compressed, what will happen is that the rubber is just vibrating, jumping, and that's actually in a way what I think is attenuating the signal, because it has that capacity to deform and to move around. Until a certain extent, I think that if it's extremely loose, you will see some kind of reflection and amplification of the signal around it.
Thank you, Joan. Please.
This type of, let's say, tool improvement of technical isolation, you're planning to apply on the existing buildings or on new one? Okay, what about with the the conditions are water saturated. Can you make the desired density in the water conditions?
Well, that's probably a question for after we do the test on site, no? We need to start with the first stage. I think that
Most of this, even this type of test, you done on the dry condition.
so far. So it's taking 10 years to characterize this material, and I think that it's taking around, as I said, 60 to 100 publications to come to the conclusion that it works in theory, and we need to see if it works on practice. And I think that PDLAC who's here today did a really good job with that 0.5 meters of layer under the building with significant lengthening of the period of the structure and actually reduction in the oscillations. We want to see all the ways of installing this material into the soil and what happens. Saturated conditions is probably one of the main challenges we're going to face.
Thank you, Johan. Yeah, I think the last question.
I'm very curious about results to show, to understand based on, the fundamental difference, that there are two distinct problems associated with this type of behavior. One is wave scattering and incoming wave speaking incident. The earthquakes are in one, which is scattered by the trench and whatever materials the trench is in. And there's, of course, the second, more classical problem of the modification of the natural period of structure due to confinement foundation. And I'm not sure what exactly you are, which of the two problems you are tackling here, because, for instance, there is not enough outer medium in this particular example you are testing. For instance, in this case to be classified as a scattering problem.
Yeah.
Although we can see clearly the tension and understand that the characterization of the material is, very, very satisfactory and very advanced. There is no reason to question the characterization, but the fundamental problem we are trying to solve is a little bit confusing.
Well, I presented 3 different branches of the GSI system, if you remember from the beginning of the presentation. So actually, we are looking at 3 different ways of implementing this kind of material or other technologies. The one where we come from is more a type of lengthening of the period by changing the foundation conditions, as you were mentioning in that case, by adding a material under the structure. This one is more a wave scattering type of problem. We are going to see it on site by adding this trench 2 meters apart from the structure. So you can actually see the configuration here.
There is not single box. Do not allow scattering.
Yeah, I mean, that was a preliminary type of analysis to see what happens with actually adding this material. So in that case, I think that it wouldn't follow or be under just strictly the wave scattering. I think that there will be a combination of soil structure interaction plus some form of wave scattering.
This is a very interesting topic, and
Thank you, but we can have a conversation after.
I have many curiosity too, but I think we can discuss during the coffee break.
That's what I'm here for.
Yeah.
Okay. Thank you very much.
Thank you, Johan. Whether sure. We move to the second presenter, Daniele Lozano, please. The title of this second presentation is 3D shaking table test of a full-scale 2-story building with fiber-reinforced elastomeric isolator. Thank you, Daniele, and the floor is yours. Please remain more or less into 15 minutes and a couple of minutes more of questions. Thank you.
Okay. Thank you, Mr. Chair. Thank you to all the attendees for being here, joining this session. I am Daniele Lozano from University of Napoli, Federico II, and I give you a short presentation on a 3-directional shaking table test campaign on a full-scale building base isolated with elastomeric isolators with novel base isolation units. Here you can see an overview of the user group, and that's not my pointer. Okay, and all the user group were let's say came from all around the world, including research institutions, universities, and some industrial partners, with LNEC providing translational assets. Very briefly, what is the main idea? What is the aim of the project? let's say somehow is along the same line of a previous presentation, but it's not a geotech project. This is mainly focusing on structural based isolation with the, let's say, quite flexible units installed beneath the structure. And the main point is trying to foster new isolation units that could be lower cost and more competitive compared to conventional isolation. And in this perspective, we investigated two different base isolation systems. The one is made of virgin rubber with the carbon fabric reinforcement, and the other one is made of reclaimed rubber with the polyester fabrics. Both systems were installed on the same specimen. And over the last decade, we have been going through a number of experimental campaigns. We have tested different specimens at different scale, including some 1 to 3 shaking table test facility at the University of Napoli. And a couple of years ago, we also tested a full-scale specimen, but so far we had no installation on a full-scale building. There was no experimental campaign investigating the influence of the axial component because of some peculiarities of these bearings in axial direction. And so this is why we moved to design of a full-scale 2-story building, reinforced concrete building, with 2 different infill systems along the 2 main directions. Actually, we had some hollow clay bricks along the X direction and some plasterboards along the other direction. And the total height of the specimen was 6 meters as per LNEC limitations on the lab total height. And as you can see here, we have a ring beam with a total height of half a meter, where the bearings.
Can you just try to remove the video
okay.
from there? Yes, there is. And this one.
Okay, thank you, Antonio. Then you can see here, these are the 2 different systems that we are installing beneath the columns. I will name them fiber reinforced elastomeric isolators, shortly FREY. So we have polyester reclaimed FREY and virgin carbon FREY. Of course, we are not mixing them together. This is just to show the position. And what is the main difference compared to conventional laminated rubber bearings? As you know, usually we have some steel shims within rubber providing axial stiffness, thus preventing lateral bulging. In case of FREY, we are replacing steel shims with the flexible fabric so that we will have lower cost. And we usually do not provide any mechanical constraints in order to avoid any tensile stress within outer regions of the bearing under lateral deformations. So this is why the so-called phenomenon of rollover comes out. So you can see here under shear strain, you have detachment of some horizontal portion of the bearing from the horizontal contact surface. And this allows limitation of tensile stress with limited peeling stress between rubber and the reinforcement, thus allowing you for a more flexible design with lower cost. And in this case, we also adopted with the polyester reclaimed rubber, we also implemented a mixed compound with the 50% volumetric ratio of reclaimed rubber. And then okay. What about the preliminary design of the shaking table campaign? We considered the shaking table limitations in terms of total mass that were 40 tons. And we set as a design point a value of the second aspect ratio equal to 3 as per stability analysis that allowed us to demonstrate that with the limiting value of the secondary shape factor of 2.5 to 3, you will have a stable response. That means no negative tangent stiffness to full rollover, up to full rollover. What it means full rollover? Well, if you look at the left side of the slide, you will see that this is the full rollover condition here. And here is the condition in between, let's say the point where the rollover starts, and we have some detachment of the horizontal portion, and the target displacement was set at 105 millimeters, so 10.5 centimeters for a damping ratio of 15%. That means considering a displacement demand conventional displacement demand at 5% damping ratio for a target period of 1.6 seconds of 15 centimeters. What about the target period? Well, target period for low-rise buildings with elastomeric isolation systems can be challenging. And you know that when you have low mass, the stability can become an issue. This is why you have to reduce the target period. In this case, we had to find a trade-off considering a target period of 1.6 seconds. The final geometry of the bearing was a circular shape with a diameter of 220 millimeters and a rubber height of 70 millimeters, so that we considered a target shear strain of 1.5 for a displacement of 105 millimeter at the target level. Only for virgin carbon fray, we investigated higher displacement capacity up to full rollover. That corresponds usually to an average deformation of 200%. And in this case, we are assuming, yes, the displacement capacity of 140 millimeters. Actually, here is not 150, sorry, it's a typo, it's 200 millimeters. So accounting for damping modification factor, it will lower the displacement by a factor of 70%. So this is the layout of the bearings with the total diameter and total height of 70 millimeters for both systems. What makes a difference is rubber compound, as I told you, and fabric type. We did some characterization tests at the University of Napoli before moving to LNEC under both compression protocols and combined shear compression protocols in order to investigate the dynamic axial stiffness at a target design load of 100 kilonewton. And also we performed a number of shear tests with different frequency of the loading protocol, different amplitude and different axial load. You can see here some hysteretic loops of the device. And here we have equivalent properties in terms of lateral stiffness and damping of the bearings, with a lateral stiffness that a target displacement of 1.5 gamma provided a very good matching with the target value of the design stiffness, and that this value of the stiffness was slightly higher for reclaimed polyester fray compared to virgin carbon fray because of the higher value of the total height of the the latter device due to higher thickness of the carbon fabrics. In terms of damping, both of them were high damping devices with the value ranging from 15 to 19%. So in the best cases here, with the virgin carbon fray, we attained 19% equivalent damping ratio at target displacement. This is a slide providing you some idea about the gravity load design, because we did not consider provisions for let's say reinforced concrete building in seismic areas because of the need to provide the effectiveness of base isolation for, let's say, existing buildings, and at the same time to comply with the Italian provisions that will not require, let's say, capacity design criteria for base isolated buildings. So it means that if you look at the reinforcement details of the cross-section of the elevation beams and columns and the foundational beam, you are going through a constant spacing of the stirrups and lack of internal legs. That means that is not the seismic design of the reinforced concrete building. And then we investigated the two-story building through numerical modeling, numerical simulations to find the dynamic properties of the building in the two directions. We found a different fundamental period significantly affected by the role of the infill partitions. You can see here the two pushover curves for the two directions. In terms of strong direction, the X direction along the brick infill walls, we found out that the stiffness and the strength increased by a factor of 3, around 3 compared to the bale frame along the other direction, that is along the Y direction where we had only plasterboards. And these are some pictures of the construction process here at the LNEC. Here we have the pictures of the two isolation units delivered to LNEC by the Italian company Italgam, that was also a partner of the project. The difference in the total height was of around 14 millimeters due to the different thickness of the quadriaxial carbon fabrics compared to the biaxial polyester fabrics. Remember that 70 millimeters in both cases was the total height of rubber. What about the construction details of the isolation system? This is a plain view of the specimen specimen on the table. And what about here? What happened in the corner beneath the column? You can see here the two systems. So for the RP fray, you will see that the unit is just left on a base plate. The base plate is a steel plate that is fixed to the table, and we are filling with the concrete around 2 centimeters of height in order to improve the adhesion and provide a concrete type adhesion. So no other mechanical connection systems. In case of virgin carbon fray, we are also installing some recess plates. That means some plates with the central hole of the same bearing diameter with just a 5 millimeter tolerance in order to provide, let's say, a restraining system that is compliant with the European provisions 15129. So that this is why we were pushing further the system under virgin carbon fray system because of the higher reliability of the system with such recess plates. About the ground motion selection, actually we did a preliminary selection based on equivalent linear equivalent properties of the isolation system with the 15% damping ratio at the target isolation period, and we were looking for ground motions having the 3 components, 2 horizontal plus 1 vertical, requiring just a very low scaling in order to avoid any distortion of the signal at the design basis earthquake. You can see here that the scaling factor were close to 1, and we selected three different ground motions, 2 of non-pulse-like type and 1 being pulse-like, the Hayashi earthquake. And we went through different intensity measures in order to account for not only for the peak ground displacement, but also accelerations along 2 main directions and velocity and Eries intensity and significant duration, so that with the 3 ground motions we were able to cover a number of intensity measure parameters. Here you can see some of the ground motions at 100% scaling for Kobe earthquake and Hayashi earthquake, that were the 2 providing the highest response. The numerical model informed the ground motion selection both in terms of target displacement and in order to control what is the resultant force at the base of the column to prevent uplift of the specimen. What about the instrumentation layout? Actually, we took benefit of all the 64 channels that were available at LNEC, installing both in displacement transducers in terms of LVDTs and optical systems to monitor the absolute displacement at the different stories, at the foundation, at the base level, at the first story and the second story level, and also in terms of story accelerations. We also had some additional displacement transducers along the infill walls and within the second story, where we had some equipment and no structural contents mounted. Well, the test matrix included more than 100 runs, so I'm very grateful to LNEC for accommodating almost every kind of test that we were designing. And at this stage, we are now considering seismic ground motion, so we are skipping the part relying on random noise that was required in order to run some preliminary characterization and also to run dynamic identification tests. But also sine sweep was very useful for this type of isolators in order to study the coupling between horizontal and rocking motion due to axial compliance of bearings. Then I will show you some results in terms of ground motion response at 100% scaling. 100% means with the scale factors plus any correction factors required by numerical models for the 2 systems. And most of the repetitions were along 1 direction and 2 directions. The 3 direction components were only imposed at 100% scaling for Hayashi and Kobe. And consider this, we had also some additional extra scaling for the virgin carbon fray because it was outperforming, as I told you. So we had an extra scaling of 20 to 25% for Kobe and Hayashi ground motions. Just to give an outlook of the performance levels, let's try to start the videos. Okay, here you can see, I'm sorry, I don't know why sometimes it rotates. This is a picture of the specimen under 3D ground motion, 100% scaling. As you can see, we have no distress along the superstructure. And if you look at the base isolation systems, you can see on the left the RP fray, on the right the virgin carbon fray. You can clearly see the rollover. For those of you who are not familiar with this phenomenon, you have detachment of the horizontal portion of the bearing, but it's fundamental to ensure stability of the bearings under very high lateral strains. And you can see what happens to the virgin carbon fray. You can see 2 additional plates. These are the 2 recess plates. Also, in this case, you have rollover as expected, but you have an additional restraining system due to recess in the steel plates. And this is why, in terms of peak ground motion, peak ground accelerations, we were able to attain 0.79 G for case of RP fray. We went up to 0.9 G in the case of virgin carbon fray, with maximum displacement of 103 millimeter and 130 millimeter for former and the latter systems. And residual displacements were very low, less than 2 millimeter and 1 millimeter respectively. And we can say that we were able to attain an operational limit state, because I will show you that also the equipment at second story did not show any significant problem. Yes, in terms of displacement, with the target scaling that is 100%, let's say, we attained under Hayashi 100% a maximum displacement of 103 millimeters that actually perfectly matched the target 105. And here you can see the orbits of the 2 systems under same ground motions, almost perfectly overlapping between each other. And if you consider some extra scaling, only the 2 at the top with, let's say, an hazard level that is representative of a maximum credible earthquake, then we attained 130 millimeter for virgin carbon frays. You can see 2 pictures with the isolators at the maximum deformation with full rollover attained. And if you ask me about the residual deformations, I can say that were negligible, absolutely. 2 millimeters for the polyester one, and less than 1 millimeter for virgin carbon. This is how the system looks like after lifting the prototype at the end of the tests. And this is what you can see inside when we try to cut. This is not a problem. There is no residual deformation. It's just a matter of hardness of the rubber and the system. So we have no damage to the bearings. About the superstructure behavior, we are interested in filtering out what is the rocking component. So what is the influence of the axial flexibility of the bearings, because these bearings have higher flexibility compared to laminated rubber bearings. It seems to be not a concern, definitely. Maximum rocking rotations were of the order of 0.1%. That means a couple of millimeters. And the same happens in terms of horizontal rotations, because no asymmetric components was in the specimen. Actually, we are still processing some displacement results because we have some spikes. Probably we have to filter out some high frequency content from signals. In terms of interstory drifts, apart from the Kobe under 20% that we are still reasoning on it, we can see that most of the ground motions did not exceed 0.4%. We have summed up about Kobe 100%. It seems from displacement measures that we were close to 0.6%, but we had no distress anywhere, no cracking anywhere. And if you look at the accelerations, this confirmed the good performance of the bearings and of the isolation systems, because the ratio of peak top acceleration over PGA was always lower than 1. So the filtering effect was achieved. And if you compare the 2 systems between each other, no significant difference, just a slightly higher effectiveness of the virgin carbon fray system because of the higher flexibility and so higher isolation period attained at higher displacements. Last slide is about no structural components and contents from inside. This is at the second story. We had a desk with a monitor above, and we have a cupboard here. We have a suspended pipe, and we have a light here. Actually, this is the picture after the old sequence, old test runs after under 20% Kobe and Hayashi. You can see that the monitor is still there. Only you can appreciate around 5 centimeter residual displacement with the length of the desk away from a couple of centimeters. This is some parameter that we also monitor through LVDTs. This is 25 millimeters. I can say that it's more than enough. And displacement along the infill walls were less than 0.1, 0.2 millimeters, providing almost negligible strains. That was confirmed by an accurate visual inspection with no cracking anywhere. So we will further analyze results also in terms of dynamic identification to check for any variation in dynamic properties. But I'm very happy about the experimental test campaign. And this is a picture of the user group with the LNEC team after the end of the test. All of us were very happy. And I would like to thank again the LNEC team for supporting us in such a challenging project. So thank you all.
Thank you, Daniele. And we are happy too. And question from the floor. Professor.
It's very nice work and congratulations. It's a non-technical question, but clearly this is like a sustainable, low-cost kind of rubber, right? Can you give an order of magnitude of how much less? Is it 50%, 90%?
Exactly. Very good point. Thank you, Gerard, for addressing this question. Based on preliminary low-cost analysis we have performed on such isolation units, we can say that we are in the order of 1 to 3. So it's around 30% less costly than conventional elastomeric isolation systems. But we think this is just a preliminary result because we have to consider what is the potentiality of a facility in providing the higher number of bearings. Now, at this scale, we are not providing such, let's say, an industrial process because it's just a handmade process and cannot take benefit of the whole process. But probably we can reduce carbon emissions, especially considering 50% reclaimed rubber. And you know that mechanical properties of rubber can be lower than virgin rubber, than ISO provisions, because we have a lower tensile stress, we have lower maximum strains, so you don't need to go around 500 or 600 maximum tensile strain in the rubber. This is why you can accept lower mechanical performance of the rubber. So, thank you.
Yeah, we just
Current applicable as well, or there should be any change or qualification test?
Very good point, Luigi. I told you about a full-scale bearing, 620 millimeter. We tested in Messina at the Eries facility, and actually we try to be consistent with the European provisions 15129, and it was almost 90% satisfactory. But the most limiting requirements was in terms of axial stiffness, as you can see. So probably we can showcase that rocky motion is not a concern when you have a vertical to horizontal stiffness ratio of the order of hundreds, not necessarily of thousands, like usually happens for elastomeric bearings with steel reinforcement. So probably we can overcome. This is my idea. And we are fostering this process of qualification, maybe through next generation of European provisions or through voluntary European technical assessment process. We are trying to discuss with the company about this.
Thank you. Thank you. Okay, thank you. We move to the third presentation. Daniele. Okay, the next presenter, Aldo Rapone, please. Your seat, and the title of the third research is Dynamic in situ testing of a 15-year-old friction pendulum base isolation system. Please remaining to 15 minutes, and the floor is yours. Relax. Okay.
Good evening, everyone. My name is Aldo Rapone, and today I will show you the preliminary results and key findings in the Eries FastFit project titled Dynamic in situ testing of 15 years old friction pendulum base isolation system. The earthquake of the 6th of April 2009 in L'Aquila is one of the most media impactful earthquake occurred in Italy. This earthquake and its subsequent aftershocks caused a lot of damages, economic, social, and life losses in all the territories around the city. To address the large number of the people left without homes, the Sustainable and Eco-Compatible Anti-Seismic Complexes Project, or CASE project, are approved. This project aims to build prefabricated houses with a base isolation system, and these housing complexes are divided into 19 residential complexes in the territory around the city for a total of 185 isolated slabs and 4,500 apartments. During the commissioning phase, some of the isolation system at the base of this building are tested. Thanks to the reconstruction efforts, some of these housing complexes and buildings are now unoccupied. Among them, our case study. Our case study is the building 20.4 in the complex of Arischia. Arischia is a small town near L'Aquila, and this building was chosen for its characteristics that are compatible with the available equipment required to perform the test. The case study building could be divided into three main parts. The superstructure, that is a lightweight three-story timber building with an overall height of 12 meters. The reinforced concrete slab that measures 21 by 45 meters. And this slab is elevated above ground level by 32 hollow steel columns. The isolation system is composed by 32 single curvature friction pendulum bearings, and these bearings are placed on the top of the columns. The total mass of the isolated system composed by the isolated slab plus the superstructure is around 1,500 tons. The isolator nominal values are visible in the table in the slab, and with them, the fundamental period of the isolated system is approximately 3 seconds. No, sorry. Okay. The experimental campaign could not have been possible without the EUCenter Mobile Laboratory or Mobilab, and this is composed by 4 main parts. The 4 hydraulic actuators capable of a total displacement of 500 millimeters. The hydraulic system that is composed by pump, reservoir, and accumulators. The power supply unit and a digital controller. The main challenge during the designing of the setup of this, for this test campaign was the developing the anchoring method for the 4 actuators. To maximize the force, the available force, the actuators needed to be positioned horizontally and aligned with the isolated system. In the slide is visible in the top of the slide the self-reacting frame, the steel self-reacting frame designed for do this and it is composed by 3 main parts. The 3 rings that are attached to the steel columns, 2 trusses that collects these 3 rings, and the reaction plate that was attached to the isolated slab. The actuator was positioned connected to one side to the reaction plate and to the other side to the center column ring. In this slide are visible some photos of the assembling phase of the self-reacting frame and a comparison between the 3D model and the self-reacted frame. The instrumentation layout used for the level of the isolated slab is visible in the slide, and it's composed by the 4 actuators, 6 LVDTs that measure the horizontal displacement, 2 tracers that measure the vertical displacement of the reinforced concrete slab, and 2 triaxial accelerometers that are positioned in the opposite corner of the slab. The field experiments were conducted using the displacement control protocol, the actuator, and with more than 20 sinusoidal loading histories. The complete amount of the sinusoidal loading histories is visible in this table, and some of them are single cycle tests. These tests are done to replicate the 2009 test done during the commissioning phase of another building of the same complex. This testing protocol ranging from with an amplitude of 50 millimeters to 200 millimeters, and a peak velocity of 50 millimeters to 250 millimeters. Below is a short montage of one of the tests done during the experimental campaign. In particular, this is the test with an amplitude of 200 millimeters and a peak velocity of 200 millimeters per second. Okay. Now I will show you some of the preliminary results. These results are obtained by all the raw data and minimally processed data. In this slide is visible are visible the force displacement static behavior of the four actuators. And it's visible that from actuator number 1 to actuator number 4, the big force for the maximum amplitude decreases from the actuator number 1 to the actuator number 4. This inequality in the forces suggests us to calculate the rotation that is visible in red in the slide. And this rotation was calculated starting from the raw displacement data of the LVDT number 1 and LVDT number 4. But some further data analysis is required to draw the definitive conclusion. As the last result that I will show you is the friction coefficient during the test. In this slide is visible in blue the pseudostatic friction coefficient that was calculated for the instant with zero velocity, and the dynamic friction coefficient that was calculated for the instant with the velocity equals the maximum velocity. In both cases, an increase of the friction coefficient from the nominal values of 5% is noticeable. With the data obtained during this test campaign, many future research opportunities arise. Among the first developments we indeed to follow are the study of the superstructure behavior, the implementation of filters to study the acceleration component during the test, a comparison with the 2009 test to define the aging of the isolation system from the real data, and a comparison of the experimental test with the numerical model using the nominal and obtained values. Thank you for the attention.
Thank you, Aldo. Excellent presentation. That's an impressive on-site test. There's a number of representatives that were involved in this experimental campaign, and also the CASE project is an incredible project. And the person that created the CASE project is here, Professor Calvi. There are some questions about this test and eventually ongoing new test, or something is planning for future test on that.
Future test, I don't know.
Okay,
but for sure, data analysis.
Okay, for sure, data analysis. Andrea?
Thank you for the presentation. I just want to ask a question. Do you have like the data of the friction pendulum at the beginning when it was first started, and how was the comparison of this?
Some of this data are now available, but we need sometimes to perform the real difference from the data analysis acquired during the 2009 and the actual data analysis.
Professor Calvi, if you want to add something.
Do you mind if I comment?
No, we don't mind about that. For sure, we cannot do that.
About 16 years ago, when this project was realized, was completed,
total of more than 7,000 isolated devices were used on 186 buildings. The isolation devices were produced by two different firms, so they were different. Most of them, let's say, two-thirds of them were single sliders, single surface. The other third were sliders on two surfaces. Essentially, nothing has been done in these 15 years. No maintenance. Everything everybody forgot about this. At the beginning, there were, of course, even at that time, significant difference between the initial data, the theoretical data, and the real data. Particularly, stick slip was higher. It was necessary to recheck all buildings with the real properties of the devices after testing them and the buildings. Now, this project has been possible only because Eries University, University of Washington, so applied for this research, but this has been a test which today is probably the top possibility of running a real test in a real building. This story, there were 40 devices under that building. But at the time of the construction, 11 buildings were tested in this way. But at that time, everything was, say, homemade. So it was possible only to do one cycle, because then all the, say, reserve capacity of the hydraulic system was over. There was not enough capacity of accumulating energy through gas compression and so on. Now what's been done is this, and they are looking at the results. And the results are incredibly reassuring about the the good conservation of properties, because these results are clearly in the same line as the results of 16 years ago. But with another project, it has been possible to go and check systematically all the 7,000 isolated devices, and actually about 40 of them have been taken out, these industrial buildings, and taken to our laboratory, tested in the laboratory. And through this check of all the isolation devices, it was possible to see that there was probably about 1% the isolation devices that had some minor problems, not really problems dealing with safety, but some corrosion here and there, so on, about 1%. But what has been maybe just results, I'm just giving feelings more than results, is that the result that you obtain when you are testing something on a large number, say 40 devices like here, the results are much better than what you find from a single result that you test in the laboratory. So somehow the presence of a large number of devices is smoothing everything away. Is somehow, if in these buildings, I know that there were a few isolation devices with some problem, but you did not realize it at all from the test, unless they would be able to find out. Anyway, I hope that this is not.
Thank you, Michele. There's no more time for questions. We move to Grazie. Thank you, Michele, and thank you, Aldo. The next presenter, Andrea Belleri, please. The title of the next presentation is the full-scale test for the assessment of the diaphragm capacity of beam and block existing floors. Thank you, Andrea. The floor is yours, and please remain into 5 minutes.
I think.
Okay, thank you.
Okay. So good afternoon to everybody here and online, as I see. So this is a project. It's called like DCABE, which is like diaphragm capacity of beam and block existing floors. It involves several universities: Leeds University, Bristol University in UK, in Italy, University of Bergamo, where I come from, the University of Chieti Pescara, and from overseas, Universidad Nacional de Mexico. And the testing facility will be like U Center. And partner of this project is also like a firm which is called Asdea, which is like an Italian firm that is helping the project in finite element modeling. So which is the research motivation of this project? So if we consider existing building, not design following like seismic regulations, we ask ourselves, are the floors able to carry in-plane inertial loading? Even if they are not designed to carry those loading? The answer is yes, because especially when you have like a spread lateral load resistance system, in the in-plane, the floor, they can act in plane, just developing some compressive arches that are transferring the lateral loads to the vertical lateral force resistance system. So, but what happens when we make like a seismic retrofit, especially if we want to create this retrofit from the outside, because we don't want to relocate the inhabitants. So if we design like exoskeletons or external bracing or shear walls, how are the existing floors behaving? Are they still able to carry in-plane loads or not? Then when you provide like external new lateral force resistance systems on the outside, you create like these small arches become big arches, and they will carry a larger load. And the focus of this project is to assess the capacity of existing floors, because if we know the capacity, we know that if the project is really, let's say, sustainable from this life cycle thinking approach, like avoid the relocation of the inhabitants, so allowing the real execution of the project. We are focusing on this type of floors, beam and block floor systems, typical of Southern Europe, typical of Italy, especially in the aftermath of the Second World War. These type of floors can present like a concrete or reinforced concrete overlay, and some others, they do not present this overlay. The point is that also like the critical ones without the topping overlay can carry these in-plane loads. So which are the failure mechanism of this type of system, of this arch type system? We can have like a compressive failure at the top of the key section of the arch. We can have like a shear failure at the boundary, and also like a tie failure at the bottom. Among like these three mechanisms, the critical one that we want to investigate is the B type, so the shear loading to the support. This support, you need to think that these are the position of the lateral force resistance system, the new lateral force resistance system. So, given like this motivation, we plan to do like this full-scale test of this type of building, of this floor, 12 meters times 4 meter dimension. We are still like considering like the setup with 3 or more actuators. We want like to test the most critical, so the floor without the topping overlay. We are foreseeing like a two steps test. In the first step, with this configuration, we would like to force the failure at the supports, the shear failure at the supports, and also we would like to calibrate and detect the floor in-plane stiffness. Then, after damage and the size of the floor, we are planning to remove and create a new position of the restraints in order to test the shear transfer in a single beam of the floor system, because this could be like critical in the absence of a distributing element, like we typically have at the side of the building as like a side beam. So preliminary assessment and ongoing research focused in the past on the shear capacity of these like blocks. Then we were able like to make like a test in small conditions in a real floor that was going to be demolished in 2021. Then this year we created like a laboratory test with like these two rows of blocks and three beams spanning like 3 meters. This test, of course, these tests are part of a PhD thesis that will be defended by Michele Milesi in 2 days. So I wish him best of luck for it. This is like the test that we carried out. You can see like the spreading of the deformation between like along the central beam, and these data are we are using like this data to calibrate finite element models. So these models are carried out by University of Bergamo and Asdea. On the left side, you see the first model that we are using to calibrate, to simulate the test that we conducted. Based on the results on that model, Asdea is developing a full scale, let's say, three-dimensional model of the test, the specimen and of the test setup. With this model, they are considering like three-dimensional elements, like also like shell elements for the bricks, and 3D elements with embedded reinforcement for the beams, the side beams. Based like on preliminary results, they are able like to show us the possible like crack pattern of this like test, and this is a preliminary results because it needs to be like calibrated on the results that we carried out in a, let's say, quasi-static test in our lab. So, which are like the activities that we are planning to do based on these results? Of course, we will need like to carry out the analysis of the results. We can calibrate a simplified analytical capacity model that could be used like by professional engineer. We can like define a performance objective of these floors and define like limit states. Derive like fragility measurements related to this floor diaphragm, benchmarking the finite element models, like define like accurate and simplified finite element strategies, evaluate the in-plane inertial loads in the floor from the seismic demand, and define like a simplified analytical tools for the seismic demand of floor. Last but not least, to carry out all of these activities, we still need to do the test. So actually, we can do this in September or October. We are still working side by side with the testing facility to define the characteristics of this test. So I've been short because I haven't done the test yet. Thank you, Andrea.
You know, I'm a numerical person, and I was really waiting for some analysis in this world of experimental test. And but I know I have a curiosity, so I start with my question. I know that Asdea has his own software, and they did the model with
Yes,
not
yes.
with classical Abacus or Comma.
They're using like their own software. And it's kind of impressive.
Yes, it's kind of a question. It's really nice. Okay, open question. All of you are invited to the test.
Oh, yes, of course. Yes.
Yeah.
Please.
Being patches from the field was by soil structures. We had copies on top of this page one. That we use, but I saw in some cases just orange color, so I'm sure.
So thank you. So we have like these two types of floors with and without topping. We are testing the one without topping.
Usually in practice, you can test it without one.
We have in practice, and those are more critical compared to the one with topping, because everything is relying on these bricks between the beams. But they are still carrying some loads. That's what we want to investigate.
I may have missed this in the presentation, but you're representing the inertial loads, slab level as external forces rather than body forces. So how accurately do they represent the actual forces that you have?
Well, thank you. Yeah, this is a good point. We couldn't like carry out like a full scale test as this size on a shake table. We made like some. We will use like this test to calibrate numerical models, and then we will carry some tests based like on distributed lateral force. We previously made some kind of like models. With like let's say like spread cracking, not like fixed or rotating cracking elements, mirrored crack models. Thank you.
Thank you. We move to the next one. Thank you, Andrea, again. Welcome. Antonio Ramos, thank you. The title of the next presentation is Structural Behavior of Recycled Aggregate reinforced concrete flat slabs with drop panels under seismic and cyclic action. As usual, more or less 15 minutes. Okay. Yeah, it's okay. And floor is yours.
Okay.
Speaker.
My name is Rui Marreiros.
Yeah, I know.
Was changed
Sorry. Yeah.
2 days ago.
Apologies.
No problem. I will present to you a project that is still ongoing. We also don't have yet the final prototype is being built at this time. This project is to evaluate the introduction of recycled aggregates from concrete in flat slabs and test in the real scale building the behavior of the structures. We have all these partners. Eries, it's where I come from. Then Polytechnic Milano, Imperial College, Polytechnic from Madrid, STU from Bratislava, CECIMPLAB from Lisbon. All things that will provide, that is being studied and will provide the concrete. And the tests will be made and is being built on the joint research center. So the main goal of this study is to study the response of the flat slabs with concrete that includes recycled concrete. Okay, and we also use drop panels to optimize the amount of material that we use in the floors. The prototype will be subjected to 2 types of tests. First, we will use a pseudodynamic test with 2 intensities, serviceability and ultimate limit states. And after these tests, we'll take the prototype up to failure or near failure. We don't want a complete collapse on the lab. So the introduction of the drop panels, it's difficult to see here, but we introduced drop panels to try to optimize the amounts of concrete that we use. If you see here in this graphic, this curve here is the curve with the flat slab without drop panels that becomes less efficient for moderate to large spans. If we introduce drop panels, efficiency grows and we consume less CO2. The motivation to use recycled aggregates can be obvious, but the thing is that the construction and demolition waste is 1/3 of the waste produced in the European Union. So we have a lot of waste from construction. And also we spend a lot of aggregates for construction that if we don't have it from the demolition, we have to have natural aggregates. So considering these two points, the idea is to use the concrete from the demolitions to build new concrete. What is being used most of the time now is to use that demolition waste for landfilling or backfilling operations and not to build new concrete. Okay? The prototype that is being built at this time is this 2-4 specimen with 3.2 meters in each floor. It has 3 spans by 2 spans. Each span has 4.5 meter and 5 meters. It's difficult to read there. And the solution for the first floor is to introduce in the drop panels transversal reinforcement. We use studs in these drop panels. The second floor will start without shear reinforcement, but is prepared. It has some initial holes here to be strained after the first phase of the tests with post-installed bolts. To design this structure, we consider the self-weight, a supplementary weight of 3 kilonewtons per square meter and a life load of 2 kilonewtons per square meter. The seismic action was considered by applying an horizontal displacement in each floor corresponding to a drift of 0.6%. To design these columns and these slabs, especially the connections between the slab and the column, we did 2 different models to compare, just to compare. And in each model, we consider 2 stiffness scenarios to estimate the forces. The first scenario is an elastic response, elastic stiffness. And the second scenario is a scenario where we consider degradation of the structure. And with that degradation, we are assuming 50% of the models of elasticity for the columns and 25% for the slab. From that analysis, we designed the slab and the columns, and you can see here the details of the drop panels for internal column, edge column, and corner column, and the solution that we will use on the first floor to distribute the studs. The studs will be introduced here at a distance a little bit more than 2 times the effective depth of the slab. The second floor will start without this reinforcement. The concrete mixture that is being studied by Olsin, will be produced by Olsin, will have 50% of the coarse aggregates from recycled aggregates. Okay, that is this portion here. Okay. From the previous tests that have been already made, with this combination, this mixture, we were able to have 41 megapascals at 28 days. So this will be the combination that will be used to produce the concrete. Okay? The test will be made in 2 phases. First, a seismic loading that will use a pseudodynamic test at 2 levels, a serviceability limit state and the ultimate limit state. It's expected that the building will not have a lot of damage after this first phase. So after this first phase, we'll take the prototype until failure. So the first test phase will be a pseudodynamic test where we'll put the quasi-permanent loads in both floors, but the displacements that will be introduced in each floor, we will calculate numerically, considering two numerical walls. Okay? So these walls are not in the lab. The computer will consider the stiffness of these walls to calculate the displacements that we will apply at each time in each floor. Okay? The earthquake that will be considered is this one from 2003 in Turkey. The second phase, the vertical load will be the same, but we'll have a cyclic displacement with increasing amplitudes until near collapse. Okay, we don't want a complete collapse of a building like this in the laboratory, so we will have to stop a little bit before. The application of the horizontal loads was a challenge because we had a previous test where we applied the horizontal loads on the top of the slab, pushing and pulling in this part. But this slab outside the drop panels has only 15 centimeters. So we will have to apply the loads in these two shear keys in each floor. So it will be 4 actuators, 2 in each floor, that are connected to the slab using these 3 thread bars. So the actuator will be connected here. Okay? The instrumental plan will have 150 channels, more or less, to monitorize all this. So we'll have lateral displacements and forces. You'll see after load cells in the middle of the columns. We'll measure slab rotations, and we will also have a survey in 3D before and after the test to estimate the damage. So we don't have yet this building completely built. So we have this 3D to help us understand what will happen. You can see here the column load cells in the middle of each column. This is a steel profile that is monitorized to estimate the forces, axial force, bending force, and shear force in each column. You can see also here these 2 + 2 in the other side shear keys to apply the horizontal loads. Okay, and you can also see this structure, this steel structure here, and also steel profiles there to avoid a collapse in case of something went wrong. Here, it's highlighted the inclinometers that we'll use to measure the rotations inside the drop panel and outside the drop panel. It's one of the edge columns here. Now, for the corner columns, we have also here the inclinometers, but we will also measure the variation of the thickness of the slab using displacement transducers here that are introduced in a hole that will measure the variation of the thickness. This will allow us to estimate the cracks inside the cone. Okay. So what do we want with this project? First, we use combination of material with recycled aggregates and an optimization of the structural design. And also, it will be the first pseudodynamic and cyclic tests at real scale with coarse recycled concrete aggregates to try to validate the use of this type of material in a flat slab. And thank you.
Thank you. When is the test planned at the GRC
in ELSA?
Okay.
Yeah.
Luigi?
Thanks for this presentation, which I think gives us a new way of looking at recycled material. We've been reading the last 20 years of material at only small scale. So I would be very interested to participate in it. The question is, you mentioned about shear design. Which is the approach that you use for recycling? And the next one is about flexure. You mentioned 50% of reduction in young moles. Is on any tests? And if you do that.
No, the reduction of the modules, it was very iterative. Yeah, the idea is not to have that reduction was used to estimate the forces, just for that. We of course, if we know the exact value, I don't have a correct answer for you. The idea was to reduce, to have more real estimation, but not reduce too much because we don't want to underestimate the forces. So we believe from our test that we will be below that value, but we use a value that is not too low to underestimate the forces. But I don't have a magic number, sorry. And the other question was the shear. Well, in principle, the shear depends a lot in the aggregates. Yeah? We made here in Lisbon several tests on punching using recycled aggregates now. And at this time, we have good results. Okay? So if we are able to have the same concrete strength, the resistance is not too different. Okay?
Sorry, I must disagree with that because the shear effect is going to be completely different in terms of aggregates interlocking.
Yes, yeah, I agree with you. The thing is that from our tests, when we use this recycled, the result was similar. What means that we were able to have it. If we use exactly the same composition, we have a problem with water. Okay? Because when we made some tests where we introduced 100% of recycled aggregates, and we had to introduce more water. That was bad for the concrete, and in that case, the shear or the punching reduced. But with similar strength, it's different, of course, but from our experience, it did not drop a lot. Okay, it drops. Yes, it drops.
I think that after the experimental test, they can convince you in the next workshop of Eries project. Thank you. One request before the coffee break, it's time for the coffee break, that the presenter of session 3 and 4 upload their presentation in the room in front of the auditorium, because there's just one PowerPoint uploaded now, and just to speed up yes, Francesco, you are the second one, and okay, thank you. Have a good coffee break, and thank you, everybody. Apologize for...
No. I apologize to you because I changed the name now.
But it's a mistake from there.
It would be Professor Pinho Ramos, but
your name is easy for me. Sorry. Okay, thank you.
No problem. Thank you.
Hi,
Josh.
How are you?
I take my pointer, okay?
Yeah, sure.
I forget it.
But
It's been built.
If
I want, I have some. I wanted to show some photos, but Pinho Ramos
l'ho fatto apposta.
for photo.
Grazie.
That would be a very good campaign.
You are the nicest chair ever.
Yeah, great.
You don't stop anywhere. Yeah, you don't stop anywhere.
For photos and marks, exactly.
We don't more.
I think he, and I don't know when did he ask, maybe 2 weeks ago.
I don't think
Probably he didn't have it. Yeah, now it's being casted. Already have the. Probably not. Probably not.
I don't know if.
But it's something that is providing us foundation. Because if it's with recycled aggregates, it has to be. But now you need the.
Now for the comics. I don't know.
Now it will be fast to build it. Not fast. Okay.
It takes at least 1 month, and yeah, no, it's not. Now they are working quite. But we only have to wait for the sharing. Okay. I don't know if it can. I don't remember. You remember for the second slot how many hours does it take? No, it would be 1 month, couple of months. I think it's maximum.
If they continue to build with.
Now they are constantly there, all the the last part of steel.
Because you don't have nothing internally, you don't have the so it's not all the instrumentation will be on the outside. So it must be fast to build.
No, it's just the construction. They have to do, but the last time it was a bit difficult to the load cells in the columns. But already for the ground floor it's done.
Yes.
And it will be easier for the first floor.
It was difficult to keep them in place.
It was difficult because they're used to build the column together.
No, it must be difficult to cast below the cells and
They use something like a
Minimum should be here.
it's like a yes, they use a larger phone. Okay, and then they leave some.
They put
Yes.
like that we call it. I'll say don't mind. I was trying to see if Pinuram would be here because he should be him. But he's in a Zoom conversation with Brazil because of a PhD thesis. He thought it would be fast, but the Brazilian guys don't have time. They will keep on talking, so he's still on conversation. But
for the coffee,
yeah, well, after the coffee, I'll have to go.
Μάθαμε μόλις από τον ίδιο ότι το τσόνι σήμαινε απλά ένα σλάγιο για ένα πουλάκι. Ναι. Έτσι καταγωγή. Μια πολύ πατρική.
Das ist wirklich, ich finde es ganz gut. Ach, das ist echt kuschelig hier. Ein Verein.
Ja, ich mache da mal Nummern dazu. Und das ist ein bisschen anderes Feeling als da drüben. Bisschen weniger spektakulär.
Hier ist halt eher so, wow.
Viel.
Kann man auch schon mal so machen. So. Herr Roberto, nein. Frau Stefan nicht immer, oder?
Der Roberto. Ja, das klingt besser. Das nehme ich.
Du schaust mehr nach Steffi aus, finde ich. Ah.
What were the presenters actually told? Do you know? Because you are presenting, right? So, were you told 12 minutes or 15 minutes, or were you told anything about the time?
Nothing.
Nothing. Good.
No, we were told 12 minutes.
Okay.
We were told 15 minutes including questions.
Yeah.
So if within the 15 minutes, then there are no questions.
Yeah, clear. I just wasn't sure if it would be fair to kind of give a warning at 12 to kind of indicate, because it would be nice to discuss, right? I'm kind of missing that a bit.
Happy. Sharing.
I have no idea. Good question. But I've been wondering all the time for whom we're actually recording.
It's in high close.
Yeah. Ciao. Does Felipe want to be called by his entire name? Do you know? How do you call him? Hey. Are you kicking off the session even, right?
Yes.
I'm still missing 2 presentations, so I've put the numbers to it
Okay,
now, so
yes.
it's easier maybe
Yeah,
to find.
exactly.
But I can also open it if you.
Yeah, just to check.
Yeah, sure.
And do you have a pointer or something?
I have one personally, so I can connect that one.
I mean,
Yeah, you can walk around. It's easier, right?
yeah, precisely.
How officially do you want me to introduce you, Philip? We already discussed that kind of the small setting takes away the formality of the entire event.
Sure.
So let's see. Let's get this connected, then everyone can use it.
And we can also change from there, right?
Yeah. I don't know.
But there's just this delivery USB.
There you go. So,
All right.
yeah.
All right.
get started, and then on slide 3, we will realize. I thought it better.
So from when do you know Bernd and Frank?
Ich glaube, das erste Mal so, die
Ja, Deutsch.
Das war damals nach der CWE-Konferenz in Hamburg. Das war ja so eine Art Kurs.
Ja, da waren noch Studienhelfer mit dabei.
Genau, ich glaube mal, welche ich schon mal gesehen.
Ich habe auch alle Events mitgenommen, ne? Von der schönen Bootstour bis hin zu dem Ratskeller, glaube ich.
Das Ratskinder war immer schon, da hast du Partner damals.
Ja, war
Interessant war für uns von außen kommen, Uni Hamburg. Die UAH, irgendwann so, ich liebe tun sie nicht.
Nee. Ja, ich meine, das drauf an, ich meine, ich glaube, ich habe selber auch wie nennt sich das dann, Wahlfach, glaube ich, dort gehabt, weil es im Endeffekt auch so ein bisschen die Nahbarkeit und halt Hydrologie studierst, wenn du Windland endest. Du bist halt kein Civil Engineer, aber das haben die halt an der TU in Hamburg. Und da haben sie halt viel mit Schiffsbau natürlich und auch viel mit Windenergie. Also das sind eigentlich ziemlich viele so ein bisschen abgedriftet in Studien. Kennst du Fries und Kitsch? War auch ewig lange in Hamburg mit
aber
dem
naja, wenn du bist, dann werden es, seitdem weiß ich, was es auf den Blasen heißt.
Ja, ich frage mich mal so überraschend viele, was so die alternative Szene in Hamburg. Ich frage mich manchmal, warum man das so viel weiß, wenn man selber eigentlich nicht unterwegs ist. Aber
also ist das, das war wieder ein Januar, ja Kontakte. Aber
ist auch mal gefehlt, ja. To be continued. Hey. That's correct, there are 2 presentations.
Yeah, and Jared said that the person is singing.
Yeah, yeah, I know her.
Have you seen her?
Yeah, she's been around, and I think she will also hopefully be back in I told her she's overturned. She went back to the hotel.
Okay.
Visit.
Okay.
So I actually did expect. She also said she wants to try her presentation. So I haven't seen her since.
She arrived.
But she has arrived, but she also has left again.
Okay.
But if you want me to, well, hold your horses. Hold your horses. I know.
Selbstverständlich. Alle. Erste Lösung. Beide Folien. Echt?
Ah, okay, das ist gesagt, dass
Sustainability. Ja, das gefällt ihm richtig gut.
Ja, aber es ist ja auch so. Ja. Und vielleicht ändert. Und die Zeit
Yeah. We can that's interesting. Yeah. It becomes under. Yeah.
Well, we haven't even started. We are already late.
So we are starting late.
We're starting late, so.
Oh. Yes, I was thinking to be things, but.
Nein, ich habe da keinen Bock drauf.
We just start.
Yeah, I'm giving, I mean, I know that Maria is going to run.
Ich weiß ja nicht mehr, wie der ist. Ich weiß, wo meine Dinge sind. Die sind bekannt. Aber du weißt nicht, wo deine sind.
Mein Problem.
Das kann ich. Ich kann
Ich bin überrascht, das ist schon ein Jahr gelangt. Die ganzen Spannungen.
Ja.
I never start here.
All right. Well, welcome of this last session of the day. I have the honor of chairing it in a more conventional setting, not so fancy than the auditorium. We are currently missing still two speakers, but I've seen both of them, so I think they will just drop in late, and we will adapt a bit of a different order than the one that is mentioned in the program. But we will kick off the session with Luis Philippe Sanchez Castro from Knutty Hansen in Denmark.
Right. Thanks. I will present the results by the user group Eries Polish. And the team is composed by Joao, Guillermo, Tristan, and Yerli and Stephanie. Well, the outline would be a short presentation of the user group, motivation of the project, what is Eries Polish, what are the objectives, a little bit about the wind tunnel measurements and the initial results. Well, the user group is formed by Kay Hansen, which is a ship designer in Denmark. From there, it is me and my colleague Tristan from Blue Oasis. We have Joao Guilherme. It's a consultancy firm here in Portugal. From the Netherlands, we have Damen Naval, it's a shipyard, and Eindhoven University of Technology, where we have Angelia and Stephanie. Kay Hansen is a company with almost 80 years, where we design from ferries, ro-ros, containers, up to icebreakers. Typical sizes of the vessel that we design is between 200 and 300 meters and up to 15 stories height. A vessel of 80 meters for us is a short vessel. So just to keep in mind. And well, part of our market as well are like the offshore wind turbine installations, where we have designed also like the largest offshore wind turbine installation in the world. We're located in Europe, in the US, in Australia. And Blue Oasis, as mentioned before, is a consulting company focused in industry 4.0 methods, where their market is mainly in the offshore, maritime, and underwater noise business. Damen is a shipyard with about 11,000 people in all the continents. And their key business is the design of tugs, offshore vessels, military vessels, air jetting, and operation and maintenance. Well, the other part is the MCV, where I think in another presentation will be they expand more about like how the internet is. This is a mock-up of the vessel that we choose for this project, which is based on the offshore supply vessel. Motivation. Well, exhaust gas emissions from ships are a problem on board. Some studies have found that contamination or air contamination in a ship is up to 20 times larger the contamination in a large polluted city. There's a lot of exposure on open decks. It affects the air quality by contaminating the HVAC intakes, and therefore, like the accommodation and operation areas inside the ship are affected. As a project, R&D project conducted by Damen, Kay Hansen, and Blue Oasis, we were like trying to limit the exposure of exhaust gases. We want to design vessels that fulfill environmental requirements, and we want to increase their operability and reduce warranty costs. But also looking ahead, right? There are vessels that are going to operate with ammonia, with LNG, with methanol, tankers that transport other type of gases, and therefore it's relevant to develop methods in CFD that can predict, how gases are dispersed and correlate and validate those results with measurements. Eries Polish stands by pollution, atmospheric boundary layers, interaction, and ship emission data. And well, here the motivation was to study the influence of different atmospheric boundary layers on the ship's exhaust gas dispersion. Have a mean of quantifying the risk of exhaust gas dispersion when the ship is at open seas, ports, the proximity of urban environment, and other relevant infrastructure. Apply and research and investigate and apply different industry 4.0 methods for ship design. And the goal is to allow
European companies to design efficient vessels that fulfill like stringent environmental requirements. We are competing against companies from China, which are cheaper than European companies and shipyards in Europe. And we have to design vessels that can operate and compete, by adding value. And the expected outcome is to improve the prediction of the ship performance. The objectives of the Eries evolution, like the first one was to investigate the effects of gas dispersion on an isolated vessel. Second objective was to investigate the influence of ship-ship interaction. And the third one was to investigate the influence of the pollutants of the ship nearby a harbor structure. To do this, well, the first step was to perform some wind tunnel measurements in TUE, where like the different angles were like tested for like, as I said, for like an isolated vessel, then like two vessels, and then like the vessel and an harbor structure. The gas was measured with an ionization detector. But later on, I will show like the different probe locations, and the exhaust gas was well simulated as a composed gas of synthetic air, helium, and ethylene. The atmospheric boundary layer was created by like vortex generators and rock acceptance. Well, here we can see like different locations where the probes was programmed to measure and sample. And here's an schematic of the different testing setups and for the objectives 1, 2, and 3. So it is worth mentioning that well, the project, the Eries project, was just to perform the wind tunnel measurements. The research and development project, which is not part of Eries project, between Damen, Knut Hansen, and Blue Oasis, is to correlate those results to the CFD simulations that we are going to perform later on. The measurements were performed like in September, October of last year. We finalized, or we got the final results like in January of this year, and then we started like doing the CFD simulations. We are comparing wind tunnel measurements that extrapolated like the results of the wind tunnel measurement to full scale, and that's what we started like doing the simulations in full scale. To do that, we use a software stack of 3 different solvers, where we use StarCCM, Refresco, and OpenFOAM, with a couple of Hexpress and ANSA for measuring. Well, here's just an schematic of the domain that we use and the different machine programs. We performed initially the runs in full-scale simulations. We want to do these later on into U runs and DES simulations. In StarCCM, we use a multi-component mixture of the helium, ethylene, oxygen, and nitrogen. And in Refresco and OpenFOAM, we use a passive scalar to simulate the gas. It is worth mentioning that the passive scalar technique implemented in Refresco and OpenFOAM differ a little bit, where Refresco takes into account some buoyancy effects, but not the temperature effects. Well, this passive scalar is used to track the ethylene gas. The conditions that we use is like a ship that is operating at 25% of engine load, because that's like a condition where the gas is supposed to be more stagnant and the vessel is not moving. To do this, we use like a reference speed of 10 meters per second, an angle degree, inflow angle of 15 degrees. The reference height is the exhaust height, which is 20.2, and an ambient temperature of 15 degrees. Exhaust temperature is also 350, and the jet speed is 8 meters per second. We started by checking that the wind profile that we get is comparable to the experimental results extrapolated to full scale, but also like the log low and the power low for the wind profiles. Here, we found that the results obtained with Star CCM or Fresco are like closer to the experimental and the theory, and we get like some sort of large deviation. The results obtained with open form. Then, we need to quantify. Another thing is helium composition was like 60% of the amount, accounting for 60% of the composition of the gas. 20% was ethylene, and then the rest was nitrogen and oxygen. So we wanted to track like the composition of helium. We wanted to check also like first how the results differ between the three solvers. And it's worth mentioning that, this is just what you can imagine. The exhaust gas is unsteady effect or something like that. And this is just a standstill of the exhaust gas cloud. To do that, we sample and probe for the gas of helium at different locations. And as you can see, like some results differ due to the techniques of the passive scalar and multi-component gas, and also like a passive scalar here with open foam. But this is just looking at the last iteration or one iteration. We have to correlate that to the experimental results, and we get like a quite large deviation in the preliminary results. We think we have to quantify that concentration of gas, not only for a small period of time, but for a larger period of time. And then, we think that probably we're not going to get like the same quantities, but the tendencies of the large peaks, we're going to be able to match better to experimental results. Another thing that is relevant to keep in mind is that the experimental results were calculated in model scale, and then they were like extrapolated to full scale. And we are having here like the parts per million, and then there's some uncertainty there in that extrapolation. Conclusions of future work. We performed the concentration of the measurements of the exhaust gas dispersion of the TUE wind tunnel measurement. Initial results for only 15-degree angles were performed, where we under-predicted slightly with Star CCM and with Fresco, and the results from OpenFOAM deviate a little bit more. The concentration values, there's like a quite like a mismatch, and for further work it needs to be done there. There's quite difference between the results found with this software stack that we use. And however, knowledge gathered from these studies are already being implemented in our design process. And we need to do this going forward, do this into the URANs and DES campaigns. Well, that's it.
Thank you very much. Apparently, we don't have really time for questions, so please find Felipe after the session or at dinner, or me if you want to speak more about the experimental results. The next speaker is Maria Pantosheva from Gate Institute. Is your presentation on there? Somewhere? Is your presentation?
Yes.
Couldn't find it, but maybe you find it better. Oh, no, is it too? Yeah, for the pointer.
Thank you. I will present you a project called Valor, which aims to create a high-fidelity dataset for validation of urban ventilation and pollution dispersion models. And in particular, I will present you a brief overview of the project and the first steps which involve the geometry preparation. And the first step on the agenda is introducing you with the research team. It consists of 3 institutions. The first one is Gate Institute from Bulgaria, which is the first dedicated big data and AI center of excellence in Eastern Europe. And it conducts research in different domains, one of which is called Future Cities, where we use technology, data, and modeling to support urban planning. And we also create city digital twins to support the design and analysis of the entire urban ecosystem. Next, there is the Digital Twins City Center, hosted by the Chalmers University of Technology, which is a Vinnova competence center focused on large-scale digital twins for urban environments. And they have experts from multiple domains, including AI, data capture, and simulation. And they have a lot of partners in the industry, in the public sector, and they drive the built-in environment digitalization. And finally, the institution without which this project would not have been possible. This is the Eindhoven University of Technology with their atmospheric boundary layer wind tunnel. And the representatives from each institution bring various background. We have experts in uncertainty quantification, verification, validation, computational fluid dynamics, and physics-based analysis, computational and applied mathematics, and urban scale digital twins. And of course, the expertise that comes from the wind tunnel experts. And I want to express my sincere gratitude towards Stephanie and Anjali Jayakumari for their constant help and support throughout this whole process. And it's only them here because I haven't met the rest of the team yet, but a very valuable part of the research team will also be the technicians at the tunnel and the lab workers. And I also want to mention that Vasilis Nasarantini is also at the conference, so you can also reach out and chat with him. And why we decided to start this project, I don't think I need to explain to you how big of an issue urban air pollution is, and it affects the environment, the economy, and human health, life, and the overall quality of the living. And the pictures you see here are taken from Sofia. Sometimes it looks like this. And the air pollution problem is pretty obvious. The biggest source of this pollution problem is the traffic. But these are also pictures from Sofia, and some of them are taken even from the same places. So it's up to us to decide which ones do we prefer to see. And since both GATE and DTC are focused on digitalization and tech solutions, we decided to find a solution that combines urban digital twins and data spaces. And starting from the physical city, the thing that we need most to perform any analysis or simulation, this is the data. It can come from various sources, but probably the best option is the data space. This is the concept, you can think of it as a one-stop shop for data, where different stakeholders, which can be municipalities, governmental organizations, industry, private companies, or even the citizens, they can share their data in a secure way with added value, and also under their own conditions, and making sure the data is interoperable, because this can be a huge problem with all the different formats and so on. So GATE has created also one of the first data spaces in Europe, urban data space, which is certified by the International Data Spaces Association. And having the data in the city, we can create a virtual replica of cities where we can monitor, simulate, analyze, and even perform what-if scenarios of the actual processes in this city, and in this way find a way to better control them. And going back to our problem with air pollution, it can also be incorporated, such analysis, in the digital twin. And one of the ways is using computational fluid dynamics. However, these type of models should undergo verification, validation, and uncertainty quantification procedures, so that they are not just colorful pictures, but we know how much we can actually trust the results. And in practice, validation means to compare the model results with physical measurements, but we don't usually have such physical measurements. And this is where such existing validation databases come in place, and they are extremely important. The best case scenario is that they follow real urban geometries with an adequate level of detail, and they are also reported with an adequate level of detail so that we can quantify the uncertainties. And for pollution dispersion and overall urban ventilation, such databases are almost non-existent. So we wanted to contribute in this regard. And via this wind tunnel testing experiment, we want to create such an open validation database for pollutant concentrations, and also a best practice validation protocol for urban modeling. And we'll disseminate the results through publication, workshops. We'll incorporate them in the urban data space and in the city digital twin of Sofia. And since we are still at the beginning of the project, we have done only the geometry preparation. We tried to make a systematic workflow for this process. And the first step is region selection and scaling. Okay. We defined certain selection criteria. We wanted to filter out places with high pollution peaks caused by the traffic. And we studied the historical data for the wind and found the prevailing wind direction, because we knew that we would have time in the wind tunnel to study only one direction. So we filter out these roads that are perpendicular to it. And we also wanted to capture an area with enough urban complexity, varied building heights. We wanted to avoid areas with huge parks, for example, and areas with very deep ventilation. And this is the one that we selected. It presents a very various background with different architecture, with different public buildings inside, bus stops, pedestrian zones. And also in the middle, there is a high-rise area. And right here is a building that would be the fourth tallest in Bulgaria, which is currently in construction. And it will be interesting to see the before and after situation, because such analysis was not performed before that. And this is the main road here. It will be modeled using point source at the congestion points. And this is the wind direction. Next, once we have identified the area, we needed to identify the actual extent of this area, which is related to certain considerations involving the blockage ratio, which is the relation between the projected area of the buildings and the projected area of the wind tunnel test section in the perpendicular direction of the floor. It should be kept below 5% to avoid any artificial accelerations. And we also considered manufacturing limits while still preserving some relevant detail on the buildings and capturing an adequate area. And the final scale that was selected was 1 to 350. Next, we wanted to set some requirements, even in this early design stage, that would be followed throughout the process to avoid any issues. And the first one are related to the level of detail that is captured. So we decided to take a strategy where we systematically increase the level of detail, starting from the edge of the turntable into the region of interest, which is in the middle. And the measurement points are located basically at this area. And when I say level of detail, I mean by the definition according to the International Classification of 3D building models and compliant with CTGML standard. So you can see in the blue and yellow zones, we have level of detail 2.2, and for the outer areas, we have more simplified buildings, which correspond to level of detail 1.3. And there are also certain requirements and best practices related to wind tunnel testing, manufacturing, and simulations. I will not go into detail now, but the main idea that you need to know is that we wanted to use the same geometry for both the tests and then the simulations. And for the actual geometry creation process, for the initial data acquisition, we didn't have a readily available 3D model, so we had to start from scratch. And this included using 2D contours of the building footprints from cadastral data, digital terrain model with elevation data, high-resolution aerial orthophotos, and also we reconstructed some details using available aerial and pedestrian level images. And the actual process of geometry preparation starts with creating the terrain. We imported the raster datasets into Rhino Grasshopper using the Heron plugin. Then we regularized the terrain meshes with QuadriMesh, and the resulted NURB surface was clipped with the extents of the study area, and the solid body of the terrain was created. Next are the buildings, and their footprints were draped onto the terrain, optimized, and touching buildings were combined, like in here, this is considered one building, for easier management. They were then extruded to their relevant building heights, and rooftop details were added, and you can see the before and after situation adding these details. This was the initial geometry creation, and then it was exported to the geometry preprocessor of ANSYS because the simulations would then be performed there. And after discussions with the wind tunnel experts, we realized that we need to flatten the terrain surface to facilitate the measurements. So we did that and also checked and cleaned some issues and geometry errors that would cause problem later on. And finally, the preparations which are characteristic to manufacturing and CFD simulations. Starting with the physical model making, we also needed to put some labeling on each building that we see scorched here, and the same labeling should correspond to a labeling at the base plate so that they are perfectly aligned. And also alignment should be ensured to the traverse system and the measurement points. And the preparation for CFD simulations, we created different groups for easier selections and boundary conditions assignments for the modeling. we performed some preliminary mesh checks, which involved mesh statistics, so that we know whether later on the simulations would be manageable with the resources we have, and also mesh quality metrics. And we also performed some preliminary simulations so that we are sure that there are no geometry issues that are not identified on any of the previous stages. And at a conclusion, I can summarize that the Valor project goals consists of creating an open access database for wind engineering data and pollution dispersion, and sharing best practice, validation, and predictive capability estimation protocols. And the specific goals of the paper that we have submitted to the conference include the geometry creation and preparation workflow that you already saw, that creates a geometry suitable for both wind tunnel testing and CFD simulations. And we try to report the whole process in detail so that other researchers and practitioners can replicate, adapt, and improve it. And just take away that geometry isn't just the starting point in the design process. It is an extremely important step which can save a lot of time afterwards and is the foundation of building trust in modeling. As next steps, we still have a few things to tweak on the experimental campaign setup. In parallel, we are running the CFD simulations. And next week, we are starting with the wind tunnel testing. And once the results are ready, we'll continue with the data processing, dissemination, and the actual release of the database. And we'll continue with maintenance and support. I would like to thank you for the attention. Hopefully next time on the next workshop, we'll have something more to present. Thank you.
Also, Tomer, it's dying to have a question. I would like to have it after the session.
Okay.
Just in the interest of time.
Yeah.
Sorry for that. Next speaker is Felix Neto. And he's making very good use out of the Eries project because it's the second time you're presenting today.
One has to.
Exactly. You're on there?
Oh, they didn't put it in the.
Is it on the
Maybe.
Want to put it on again? Can I leave it on the desk or you mind? Do you need the presenter? Or are you good without presenter? Because otherwise I put it off.
I don't know.
Do you want to put it away from the disk or put the presenter back in?
Oh, that's fine. It's up to you.
Just do it. If you don't need a presenter, we can run it from there.
Okay, yes. Okay. Here we go. Good afternoon. So this is the presentation that I have. The title is Effects of Small-Scale Turbulence on the Aerodynamic and Aeroelastic Responses of a 3:2 ratio rectangular prism. So this is a collaborative research by the University of Sydney, Kenny Kwok, University of Bologna, Luca Patruno, University of Coruña, and of course, the host institution, University of Genoa, and very remarkably, Giuseppe Picardo, who is taking care of the tests. So the outline.
Not connected because.
Okay, so by hand, no problem. The outline of the presentation is this. Let's start with a an introduction, a description of the wind tunnel testing campaign, and some results for the flow characterization for the rod that I'm going to explain, and also for the aeroelastic response of the rectangular prism. So here I have a disclaimer to do, which is that the results that I am going to show, they are still warm coming from the bakery, because these tests were conducted just last week. So we are really in a very preliminary stage of reviewing and making sense of what we are getting here. So the motivation for the work, let's say that this is a project a little bit different from some others that we have been seeing during the day, because this is kind of quite fundamental things. So the focus here is on turbulence, small scale turbulence, large scale turbulence, and the application case is, as I have just said in the title, the rectangular prisms, the ratio 3:2 prism. So, and I would also like to mention that we have another project funded by the Spanish Ministry for Science and Universities, which is addressing the CFD simulation of the kind of responses that we are also testing in the wind tunnel. And we have the hope of using also the results in the frame of the validation of our CFD simulations. So what we are really interested in is the aerodynamic response for the prism, and also the aeroelastic response, mainly galloping in the Heath degree of freedom, when we have different levels of turbulence intensity and different length scales in that turbulent flow. And this is an information that is relevant, of course, from a fundamental point of view, but also in the context of energy harvesting applications. So I am going to refer here for the types of flow that we are going to be working with. Of course, we are going to have a smooth flow, but we are also going to have what we are calling here approach 1, which is this large-scale grid-induced turbulence, which, of course, all of you are familiar with, and the not-so-common approach 2, which is the small-scale rod-induced turbulence. And I would also like to comment that there has been some work done in this particular geometry by Nguyen for the fixed rectangular prism in smooth flow, and also by Manini with large-scale turbulence, fixed and galloping responses of the prism. Okay, so let me explain a little bit what is this small-scale rod-induced turbulence. So essentially, this all comes from 1973. The work by Garshore when he was doing a research stay at Western University. He was the one who first proposed this approach for generating a turbulent flow in the context of aerodynamic studies. So essentially the idea is, okay, let's place a rod, a small diameter bar, upstream of the body we are interested in. We are going to generate a turbulent wake, and this is really the turbulent flow that is affecting the black body that we want to study. So in words of Garshore, in the report, he's saying that the idea that only the turbulence close to the upstream stagnation line of a black body is effective in modifying its flow patterns suggests that the use of a thin wake produced by a narrow rod located upstream of the center line. So he explains that the wake will introduce roughly isotropic turbulence of a measurable intensity and scale, both of which could be changed by moving the generation cylinder with respect to the black body. So essentially, what Garshore is telling you is, okay, I have a turbulent wake, small scale, I can control the turbulence intensity depending on the distance from the rod to the body. So that is the very fundamental idea. And he conducted some tests for the square prisms, and things were working nicely. And eventually, he finally suggests that the success of the thin wake in altering the characteristics of the black body, apparently as effectively as grid turbulence will do, suggests that this method could be used in further studies of the structure. And this is true. This is what is published, and we have to recognize that obviously grid-induced turbulence is the most popular method so far, and the applications of this method have been relatively modest. So mainly work in a couple of cases, and more recently, for instance, Lander and co-workers from Rensselaer University have used this approach. For instance, ourselves, we used this in a CFD paper in 2023, published in Journal of Wind Engineering, but with a CFD idea or objective. So let's then go into properly the tests that we have conducted, of course, in the Giovanni Solari wind tunnel of the University of Genoa. You all know the characteristics of the test section is 1.7 by 1.35 meters. And we really were very interested in this facility because of the low turbulence. I mean, the high quality of the flow was something very important for us since we were focusing on small scale turbulence. For this project, the model, the rectangular prism, is made in carbon fiber. The dimensions are 9 centimeters by 6 centimeters. There are 9 strips of pressure tabs along the rectangular prism, and the balance and pressure scanners are sampling at 800 hertz. Displacements and dynamic tests are measured by laser sensors with a frequency of 2 kilohertz. And the flow velocity, that is very important for us, the characterization of the flow, is made by means of 4 X-wire probes sampled at 8 kilohertz. So the scope of the project is to, on one hand, characterize the flow, of course, the smooth flow, the turbulent wake after the small rod, also to characterize the flow when we have 2 different sets of grids to generate this large-scale turbulent flow. And on the side of the aerodynamic response, we are going to be testing the static, the fixed rectangular prism and under those different flow conditions. And we are also going to focus on the wind-induced response in the Hip degree of freedom. So in principle, the galloping response. And there is a 4th stage here, which is at the very end, we are going to try to make a proof of concept to see if we can really use also this rod concept and this turbulent wake as a mitigating strategy for flow-induced vibration. So we are going to give it a try. So going into the results, this is my first picture. This is focusing on flow characterization. So you can see here this black line, which is essentially the rod. It's just a 5 millimeters diameter bar. And you can see here the traverse system with the X wires in order to take the measurements for the flow characterization in the wake of the rod. And this is what we got in terms of flow characterization in the wake of the rod. So perhaps this is a little bit complex. Let me explain a little bit. So here in this first chart, what you have here is with the distance in the wake of the rod, the turbulence intensity profile that you may see that is decaying. From very close to the rod, you have relatively high turbulence intensity, as you may see, almost 25–30%. But this quickly decays, and you can have values around 10, 5, 10, 6, 7, and you go down up to more or less 3% turbulence intensity. So you can control the level of turbulence intensity that reaches the black body depending on the distance between the rod and the rod. And in the same chart, what you have here is the evolution of the mean wind speed. So obviously, when you are very close to the rod, you are obviously sheltered by the rod itself. So with a reference velocity of 10 meters per second, you are around 9 meters per second. As you are moving downwards in the long wind direction, you recover the reference value of the wind speed around this 10 meters per second. So, I mean, there is no relevant sheltering effect for the flow really impinging on the black body. So, for instance, this is just the time history of the velocity, where you can see obviously this turbulent content in the wake with obvious fluctuations in the velocity magnitude. And this is the spectrum, whether you, of course, you have here the vortex sharing signature for the rod, but you may see how you are really reproducing the turbulent content with the decay of the energy. as it can be expected. And finally, this chart is just to understand a little bit. This is really a vertical profile. So you have here this theta variable, which is really the vertical profile. So you can see how just when you are in the wake of the prism, the turbulence intensity, it's just a second. It's very, very high. I mean, because you're in the turbulent wake, in this case, 8% turbulence intensity for a position which is 20 centimeters in the wake of the rod. As you are moving, let's say, upwards, so you are getting out of the turbulent wake, so you are finally reaching a smooth flow, just 66 centimeters from the wake center line. In terms of the mean wind speed, which is the blue curve here, when you are just in the wake, you are sheltered by it with around this almost 9 meters per second, 8.6. As you are moving upward, you very quickly go to the reference velocity of 10 meters per second, just a few centimeters from the axis of the wake. This is in terms of flow characterization. This is the system identification properties, the decay, the natural frequency for the Higgs degree of freedom. This is the torsional natural frequency for the prism. So this is the characterization of the dynamical system that is going to be tested. And this is a video, of course, in slow motion, precisely of the wind-induced excitation of the rectangular prism, in this case, in a smooth flow. So what are you getting in terms of results? Moving from just the video. So here at the right, you have the evolution of the Higgs response depending on the reduced velocity of the flow. So you can find that we essentially are getting the typical plot where, as the flow speed increases, also the Higgs response of the system is increasing. In fact, at the very beginning with obviously very, very low amplitude, as you can see here. For higher levels of wind speed, what should be the reference, the critical wind speed, we have a higher Higgs response in this case. In fact, you may see that the ideal vortex sharing frequency is close to the natural frequency of the system. And if we are moving to higher levels of wind speed, for instance, here we have a more clear response in the dynamical system. Eventually, we are reaching a peak response with a very clear and sustained oscillation here. And afterwards, what we are getting is this kind of plateau here with no really increment in the response, nor decay, neither. That is something that we still are working on. So we have some, let's say, persons of interest. In fact, the damping ratio may be playing here a role, but this is something that we are still discussing. So you can see how essentially we are keeping an almost uniform value of oscillation around 6 centimeters, sustained excitation, but we still have to work a little bit on this issue, obviously. Just to complete the report of results, so very quickly, here we have for, in this case, this particular value, the results of the mean pressure distributions and the standard deviation of the pressure coefficient for the 6 strips of pressure tabs that we have in the prism. So you may notice that essentially there is a very good uniformity in the response with the 6 strips providing pretty much the same results for the mean value and even for the standard deviation with very little differences here. And here, for instance, at the peak response, this is what we are getting with, it's obvious let's say the organizing effect that the higher amplitude of oscillation is having with almost identical values for mean pressures and even for the standard deviation of the pressure coefficient, which is something that tells you that things are going as well as they should. So just to conclude, let me summarize that we have been working on this project, in this focusing on the effect of small-scale turbulence so far, with a very good characterization of the flow in the wake of the road. That was really an important challenge in the project, I can tell you. We have also started a little bit with the characterization of the dynamical system and the heat response. As I said, this is just from last week, and we have to work a little bit on that. And we are expecting to move forward in these weeks and completing this piece of research and this project. And let me please finish the presentation thanking the team from Genoa for the very nice job that they are doing with this project. So that's all. Thank you very much.
It almost pains me to say, but please find Felix afterwards for questions.
No question?
No, sadly not. We are already 10 minutes behind, so I think for the remainder of the session, there will not be any time for questions, I'm afraid. So please find the speakers in the time in between. The next presentation is from the Technical University of Munich. It is Ann-Kathrin Goldbach. I will give you back the presenter.
Okay. Thanks a lot. So as you can see, it's not just me. So my name is Ann-Kathrin, hi. But there's also our professor at the Chair of Structural Analysis, Roland Büchner, with me. And together we will present what we've been working on for quite some time already, the wind effect on non-standard shapes and structures, namely membrane structures. And the part of that has been an Eries project, which we are very happy to have been able to conduct at the Western University together with Girma, who's sitting here. And when I say non-standard shapes and structures, what I mean by that is membrane structures. Architectural membrane structures are quite special in their unique shapes and flexibility, so they can cover very large areas and they can have a lot of different usages whilst using minimal materials. So the thickness of the material is about 1 millimeter, sometimes a little less, sometimes a little more. And then they can span up to hundreds of meters. And in order to build these kind of structures, you need to be able to find an equilibrium shape, because this only works if we pre-stress these structures. So that makes them even more unique, because not only their shape is very special, but also the mechanical setting and what kind of stresses and forces we induce to make them stable. And apart from form finding, there's a few other topics that need to be covered if we want to analyze these kinds of structures.
Yeah, thank you, Kathleen. So the reason why I'm now presenting these slides is that there are lots of projects several years ago. So we started many years ago with analyzing thin-walled structures, lightweight structures. And well, I could speak about each of these projects also on the next slides a lot. That's the inherent danger if you give the microphone or the speech to the professor. But I want just to mention this place here. It's a small intro also to our lab. Yeah, that's what I want to mention here. Today in the opening, it was said that we should think also what comes next. And that's exactly what I want to indicate here. So we are dealing with a lot of these structures. So these are particle methods and protection nets, high-rise buildings and wind, but especially also we are working a lot in this twinning activity, really inversion of that stuff. So I saw it just before in the talk, so we should definitely have a chat. we are a computational mechanics team. Yeah, we work in simulation methods. We develop our own methods. We have own open source software frameworks which are running. And here are just a few, well, buzzwords, let's say. This year deals with the complex shape treatment. We deal also a lot with geometry preparation, workflows, stringent and closed workflows. Also here we deal with a lot of structural optimization. That's, for example, optimized structure in civil engineering. Especially for many years, we developed methodologies, stable workflows for multiphysics simulation, especially fluid structure interaction, which is interesting, especially with wind engineering. And well, that last point here, I think that's where we are all heading to right now, because we from the simulation side, the computer people, we rely a lot on people doing real world measurements, this stuff here. And that's something where I think we have a very strong point on in these days. Everything summarizes in the computational simulation lab, which we started at TUM because we have some initiation funds. I just started last October. They're leading the chair, but it's not only me with the team at Munich, but it's also, for example, Professor Dasaro, who is already in that. And we are a transnational activity. We join forces in the simulation, on the simulation side. So this one here. But with all that words mentioned, I want just to say to you, please contact us. We can also think about next possible projects in that field. Now I opened the doors. Now I will just confine again the discussion here. So the simulation lab, or let's say what was there before, we worked already a lot in these investigations. You see, they're all very flexible structures. We had very nice projects already about flow-induced vibrations of these solar troughs or these super lightweight umbrella structures. The software, what we are mainly employing is the Gratus multiphysics, but also we have extensions and interfaces to other softwares. So some of these simulations, for example, here, were also concurrently done against, or let's say with OpenFOAM, just to investigate the different properties of these softwares. So that's my part. That's a bit the look ahead, but also making clear why this is on the roadmap. This Eries project, together with Girma's team, we are happy about this collaboration, is definitely a strong next step from this year. And now I hand over again to the project leader. Please.
Okay, so as you can see from the computational side, there's a lot of capability already existing. And apart from these projects, there has also been a lot of research activity towards the standardization of wind effects on these non-standard shapes and structures, which is again the topic of the project that we're presenting here. So for example, some of you may know the investigations that took place at our institute a while ago on these very large scale umbrella structures. Some of you may know the activities from Italy, where there are these surface pressure maps for the doubly curved surfaces. Nonetheless, even though there's a lot of activity towards standardizing the analysis of membrane structures, there's nothing on wind effects. So we are working towards a Eurocode of designing and analyzing these structures, but the wind effects are not covered at all because of the uniqueness of the shape. So it's not easy, of course, to generalize this. I just started the talk by saying they are also different and so special. But we would still like to try. So the motivation and goal and where this project fits is to try and standardize the wind effects based on generalized shapes of these structures, and to see not just for these specific shapes what happens, but to establish a process of finding out which kind of steps do we need to take and how can we approach these unique shapes, which kind of workflow works to have safe but also efficient structures. And like I said, the wind tunnel test, the wind tunnel validation is a very important first step in this approach. And I will talk about the other steps towards the end of this presentation. Okay, so which categories did we think of? We didn't have to imagine those from scratch because with all of this standardization committee work, towards a Eurocode, there had already been a few first steps established in this direction. So what we did was to take these 5 standard shapes that you can see here that were defined by the TensiNet Association back in 2015. And when they first tried to approach this problem to know more about the wind effects. So we have these 5 shapes that you can see that have all of the same pre-stress settings. So they have a uniformly distributed pre-stress in the surface of 4 kilonewton per meter, and then 30 kilonewton force in the edge cables, if there are some. And in full scale, these shapes would be 6 by 6 meters. And then towards the wind tunnel, we then have a model scale of 1 to 25, which is small models, but 1 to 25, I think, is still pretty good. And then what else can you see in this table? You see the shapes that we investigated, which are the, let's say, standardized ones from a membrane point of view. And for those, we investigated different kinds of wind scenarios. We did ABL settings for all of them. And then for the hyper, which is the most iconic one, I would say, we also tested non-synoptic winds. So we had downburst tests and tornado tests to also find out what these kinds of wind scenarios do with the doubly curved unique shapes that are quite special. Because again, there's no knowledge published on that yet. And on top of that, we also asked the Windy group to test group configurations. So for the cone that you see there with the number M4, we had a group of 3 by 3 models next to each other with the instrumented model in different positions to see what happens, what kind of effects we can see if we have a landscape of shapes, basically, and also in a row. Okay. The data that we got were the pressure time series at the tap locations, and with that we did some post-processing. So this is what it looked like. This is the hyper example, the one that we tested in ABL in a downburst scenario and tornado. And you can see there's a lot of different angles that we tested this in. It has a lot of tap locations, and I'm going to speed up a little bit. There you see some more impressions of me standing in the wind tunnel and being quite happy because I'm a giant in a tornado. And these are some first test results of the net surface pressure for all of the different shapes with the wind coming in X direction with a 0-degree angle. And then it goes on. So this is the cone model that I showed you earlier, which was tested by itself in an ABL flow, but also in this group configuration, where again, it was great to see what can be done in this wind tunnel with the different positions and moving the shapes around. This is the row, and here are some first post-processing results of the data that we have. All of the results have been uploaded to Zenodo, so this will be an open repository with all of the shapes, the descriptions, the information on how to form find these, or what the form finding settings need to be, so that you can actually replicate the exact shape and not do something on a slightly different one. Because again, what the goal would be in the end is to have something that looks like surface pressures which you are used to from the Eurocode for other kinds of structures. So the first step towards that was to do this wind tunnel experiment on all of those shapes. And apart from having those measurement results, and what we're looking for is, first of all, a validation of our own code, which is implemented in Kratos Multiphysics, but then also to compare and see what other contributions we could have from the community. So if any of you are interested in these kinds of topics, we would be very, very happy to get more input from the community too. Because what we are still missing is, like I said, more and different approaches, but then also coming back to this workflow that I was talking about, what we need to understand still is how the flexibility of these structures then affects the results. So what we did already are the CFD simulations, and we have run some preliminary FSI simulations too, but this is the big chunk of work that's still ahead of us, so that in the end we can see what the differences are, where the challenges lie, and how to approach those new questions when they come up. So thanks a lot for listening. This is the whole group that has been working on this at Tom's side. Thanks again to the Windy group also. We had a great experience. And if you're interested, of course, check out Kratos Multiphysics. Thanks.
Time for a question.
Aha.
May there be one.
What about the Reynolds number effect of the shape?
That's a challenge, of course. You're right. So this was, of course, considered, and there's been some what they did was they changed the roughness of the shapes. And I think that in the end, this is one of the questions that we have to approach. What kind of model makes sense in the end? What kind of result do we get from this small model? What kind of result do we get if we have a full-scale FSI simulation and so on? So,
Thank you again. And rounding off the session will be, yes, I know, but we just have a Picaido from Genova.
Thank you, Mr. Chairman. This presentation concerns the experimental activities on vertiports. The project is the project is a small German company, DM AirTech. Then my presentation is, of course, not complete because the experience and expertise of a company is essential for this kind of work. But in any case, whatever with Maria Pia, we think it's important today to have a presentation and show of the activity of the project. Then this is the reason of my presence here. I try to get a short and comprehensive presentation about this project. And the problem was about the urban air mobility, because is a new way also to alleviate the traffic congestion, for example, is in a way interesting. But the understanding the impact of induction on the planning design of vertiports for example, drones or similar, then the problem of vertical takeoff and landing safe is an important problem about this subject. Then the project just concern this topic. And the primary challenge with vertiports concern the aspect of the visibility, operational availability, and the safety of vertical takeoff and landing operations. However, the necessity of experimental investigation about this and above all, the effects of turbulence in general on vertiport operation seems very important. And in particular, in these slides, we summarize, for example, the existing or initial some regulation about this problem. but both the regulation, both the literature have a lack about, in general, the aerodynamic performance of vertiports. Then the aim of the project is to address this gap in the literature, how in the facts then aerodynamics consideration can influence the vertiport's location, and the objective is to obtain at the end of the project a data set that then very useful for the company, but also for the people. This data set will be a free data set, also for numerical modeling of this kind of object of vertiports. In particular, the use case are two in general, at least according to the company, to the MRTech, are surface vertiport and urban vertiport. Surface vertiport is the first slide, are vertiport located to the ground. Usually the ABL can be an open country or CABL, and the study of a project concern the impact of various upstream obstacles on aerodynamic performance of this kind of vertiport. The second, urban vertiport, concern vertiport located over a rooftop of Eries building in a urban environment, and in this case the problem is surrounding, is the vertiport shaded or unshaded with respect to other building, and also there is some effects about the position with respect to the center of the building, for example. This is a summary of the three phases of the project. The first one, phase one, is a phase introductory. We performed phase one about 2 years ago, a lot of times ago, at the beginning of the Eries project. It concerns the measurements on rooftop models, and the first part also has been used by the MRTech to preliminary database for CFD calibration. The second phase, this project with a lot of discussion with the company starts some months ago. The second phase was performed at the beginning of this year, and concern the studies for surface and urban vertiports, analyzing some different configurations, as you can see in the following slides. And the phase 3 was performed only partial at the moment, a few weeks ago, concern a PIV flow visualization in the case, on selected cases, up to now, only in the case of surface vertiport. But before to have a brief show about the results, I would like to show some exploitation that the company, the presence of the company is concerned was necessary, but I try to show in any case the company about the activity of the project. In particular, the company has some exploitation, internal exploitation concerning mainly the passenger and comfort, and about this point using some results on also about the PIV test. Some exploitation on commercial type, for example, the company had a relationship with European space about some application in complex area. Also, the company developed a software called the VertiPlace, VertiMonitor, that can benefit also the results of this kind of project. And also some collaboration, principally with the companies located in Hamburg, the first one also in a ministry in Germany and found was about the developed requirements for cities adopting drones and electric vertical takeoff and landing applications. And the second one was about machine learning technique to have a less computational time using simulation, then try to using standard simulation like runs, obtain good results also about the key parameters necessary to improve vertiports location. We don't speak about the K parameters, sorry, I forgot it before, but the K parameters usually are turbulence intensity and also shear flow. Also the shear flow is important in this case. Then you try to highlight this parameter in the next slides. About the first phase, you can see a model using in our wind tunnel for experimentation. We select 5D buildings and we perform some measurements using Cobra probe for local measurements, a pitot tube for reference velocity. And in this case, it's possible to see some velocity profile above selected buildings and also in different direction, obviously, and also the turbulence intensity profile above the same building. These data are already partially used by the company also to integrate the CFD model, as I said before. About the phase 2, we start to talk about surface vertiport. This slide, you can see the different simulation for open country sea profile. And these are the 5 different configurations or surface vertiport. The first one is isolated configuration, configuration 1. The second, I don't know if it's possible to use it. Yes. The second one is we're using a guide vein. The third using a solid barrier. The flow is from right to left. The fourth using a porous barrier, and the other using a line of trees, for example, and perform a different situation. In this case, using the 2 different boundary layers, as I said before. These are some results, but it's not useful perhaps to spend time at the moment. But results are concern the median velocity in this point, more point at the central, and also the point around the central point of the possible location of vertiports. And this was results about turbulence intensity. In this case, for a case of open country, and similar results also for a case for VC profile. And the conclusion about this first analysis was that the best configuration in this, at least in this experimentation, was the first one, the container with the guide vein. It has the highest performance among the test setups about the aerodynamics. Then you decide to continue to use this configuration and to use this for PAV evaluations. Then in this slide we present the setup we use in our wind tunnel for PAV. This for lateral section and this for horizontal section. You use one lateral section in the middle of the gate, because the container represents the gate, and after the container there is the location of vertiports, this configuration, and the other about 3 different horizontal sections. These are the results. This is vertical, is a vertical section. This is actually the position of the container. This is represents the area used by the PIV simulation, the PIV representation. That is possible to see the turbulence kinetic energy, the velocity, the longitudinal velocity, and the vertical velocity. It's possible to see behind the container the recirculation of the flow, and it's possible also to obtain that the turbulence is quite high in this region. This region is in correspondence also of vertiports. Also, this graph is related to velocity gradient contours about the 2 different boundary layers. And the contour, as I said before, is important to the generation of shear stress, and then is important value to examine the performance of vertiports. These are two animation. I don't know are working. Yes, are working. Are created by displaying the simulation is very short, only 3 seconds, and the animation are obtained using 1,500 instantaneous velocity. So it is possible to see in this animation the recirculation of the flow after, and these are open country, these are for the sea, for in different situations. Only a few words about the horizontal. In horizontal situation is similar. We have the symmetry is quite good about the longitudinal velocity and about the lateral velocity. We lost a bit of symmetry about the turbulence kinetic energy, but probably is due to the short time acquisition, only per second probably. This about the gradient of velocity, and the same graph on the second plane and the third horizontal plane. This was the phase for urban vertiport. At the moment, we are studying five configuration. The five configuration for urban vertiport are related to configuration 1 is a vertiport is in the exactly centered and pose on the rooftop of ideal buildings. Then different height and also the possibility to move towards the lateral side of the building. And also in this case, we perform some measurements using Cobra probe, and these are the measurements point. These are results about the mean velocity profile and profiles of intensity turbulence for the situation for different location. And the final results also in this case was that the best configuration we find was when the deck is positioned on the left and elevated by quantity with respect to the top of the roof of the building. But in any case, we consider the position centered for the prosecution of activity. Then the last activity we are to perform in the next month was regarding the last activity also of the project was regarding a PAV evaluation of the top of the building using this section for ending also the project. Thank you very much. I'm finished.
If there is a pressuring question on vertiports, a quick one, go.
When you say the better position, is this in what criteria are you saying better?
Yes, better position criteria.
Intensity.
Yes, using turbulence intensity, yes, and a rough evaluation of gradient, because using Cobra probe is not so easy as PAV measurements to have an evaluation of the gradient, but this for us are the key parameters. Yes, about this point. Is a individual evaluation using also DMR tech, not standardized evaluation at the moment, but you decided in this way with the company.
When you have two of the plane earlier, where was the location of?
But about
earlier, where you have parallel.
This one?
Yes, those plane. Where does the vehicle parks on the roof or on those planes? I was not clear.
In this way?
Yes.
Yes.
Like you have.
The flow is flowing in this direction.
Yes.
Then there is this recirculation behind the.
Where would be the port then? Where does
the port? Yes, the port is approximately in this position. Approximately, is it possible to see perhaps better in the slides? Yes, about 50 to 100. That about in this position. About from here to here. Yes. This is the position. Sorry, it's not indicating this slide. Sorry.
Okay, well, for further questions, I would again direct you to after session, and to conclude, let's thank all speakers again. No further information of any further plan. You're dismissed. So
Yeah.
Likewise.
This is just okay, let me that were Friday. But you don't have to keep that on the person. Yeah, but
Because I talked to Anders and we're thinking if you need us on site, me or Anders, we can be there. If not, yeah. So we'll let's figure out.
Typically, we are operational with them, the user present. There are for this project, I don't really see that any changes planning with the thoughts. They have to change the general outfit. So
Yeah,
for us, it is fine.
Yeah,
There is no value of traveling. We had a goal particularly of every one of the user group coming coming so for us it's nice of course to afford it there, but it doesn't work out.
Yeah, we'll see. Would love to be there, but both me and Anders might be.
Yeah, I mean really
Okay, that's fine. So Stephanie says perhaps tomorrow during lunch time. Okay, so after 12 tomorrow, right? Okay, then thank you then.
Yeah, I mean, I think coming back to having some present of one person whose group is there at a time.
But
Just in case, like just in case you want something that someone is there, so this usually helps that they don't have to be on the phone and then kind of. So regarding that,
we only have Saturday and Sunday that we discovered, but I guess
that's fine. We will not work Saturday and Sunday. We are not
Okay, then. So I'll see you tomorrow.
Yeah, are you trying to do that?
No, I didn't know. I thought it was on Friday, so I have other. Yeah, but I'll see you tomorrow. And I have many photographs.
No, all'inizio è titubante, poi ho detto che
Yeah, and yeah, everything. So you're living nearby, right?
Yes.
Okay. So tomorrow you're going to, I guess today. Yeah. So tomorrow after 11, then we can sit on Stephanie. Do you have anything to say to discuss or just?
I don't think there will be any.
Okay, then perhaps just 20 minutes to see. Just touch base with Anders because since I came here, he's thinking perhaps both of us going there is a lot of reason. So it's like, yeah. I mean,
There is really,
yeah, but of course we want to show face because he is the PI. Yeah, so I'm trying to, kind of bridge the thing so we don't have to do problem.
Yeah. You can also come to the next one, like this one.
When is it?
I don't know.
So you mean like after the summer? or
Yes,
something?
because for example, in the first presentation here, they did a test last year sometime, and they're presenting now. So we'll have to present another workshop again.
Okay, the results and things like that in the
He
paper.
can also come and show it there.
Okay, then that's fine. Another thing, we started writing the volume mass paper. Now we have a proper volume mass. Have you worked with GMS or OpenFOAM, Hexis, Snappy, or whatever? Then perhaps we'll use your massing skills too, because we want to benchmark. So from surface, so we create a volume mass, we extrude the surface, and we take that as input, that STL, into a real 3D measure.
Yes.
And benchmark the time, the quality, and things like that. So I guess you can help with the CFX part, right? It should be easy for you.
Yeah.
But nothing fancy, just no weird requirement, just spit it out of the box.
Do you have a deadline?
No, don't worry about that.
Okay.
We're very loose. And if you want to go to Mytilene in the summer, let me know because we're submitting a paper. But I need to know by the 15th.
With
Asimina.
When is some? I haven't.
End of July.
Yeah, probably not.
Okay, hold on. It's a great opportunity. So let me check. It's
I mean, this time I was not planning any traveling.
Due to the PhD. I'm just trying to, because you missed Corfu,
Yes,
okay?
yeah.
So it's a good opportunity. Let me check. It's 10 to 12.
Wouldn't it be too hot?
But that's the point. It's the Aegean. I mean, it's a great island. And Orpheus is there as well.
Yes, I know.
So it's a great opportunity. And Asimina will be there. So that's a great opportunity to catch up.
I wanted to visit and to see the castle.
Yeah, precisely. Yeah. So keep that in mind.
Okay.
Just a small note. Let me know if you cannot make it. Otherwise, I'll make it happen. Okay.
Okay.
Either you or Adostin.
But for me, probably not.
Okay.
But I'll
Okay. And another thing before I forget, we want to come and talk to Simeon about the 3D printing thing.
Okay.
It seems very close to what we're doing.
Yes.
And we have customers in Sweden, so perhaps we can actually use money to test it with you guys. I guess you're not
Test
really
what?
Test the workflow. Simeon has a prototype workflow that's kind of cheap compared to the full-scale thing, and we want to test that. So I think it's a good excuse to meet up. But you're not involved in that project at all, or?
No, right now I'm getting out of all of the activities so that I can focus on the PhD and then
Get back. Yeah. Okay, but if we're planning to come there for 3 days, I guess we can.
Yes,
we can arrange something. Okay. I don't know when that's going to happen, but we're talking with Anders tomorrow, and even the vice rector of Chalmers, because they want to create, apart from other things, a physical twin of the campus. Okay. And they failed to do so because it's very expensive, and perhaps Simeon's workflow is good, and it would be cool to have Gate and DCC created.
Yes.
So I'll keep you in the loop. Okay.
Okay.
Okay. Let's move on. Sorry, I don't want to keep you. How about Lisbon so far?
Mixed feelings.
Why?
I like the general
vibe. Yeah.
It's just that I have only visited this area. Yesterday I told you that I had some issues with the Airbnb.
Okay, was it because something went wrong or something?
Yes.
Okay. Yeah.
And I didn't have time to see anything other than this area. You can hear the airplanes.
Yes. I mean, we went downtown and we had more time today. I think we were today. But it seems like nice city.